notebook. This is a very basic notebook that speak about the cryptography or the so let's just go with it. The classical this is the Paris notebook we have. It speak about
Instead of battery, I'm sorry, battery.
I think you have to speak louder. I have to speak louder.
yes. I think so we have this first notebook. So this one speak about the secret key cryptography and
Louder, please.
yeah. So it speak about the secret key cryptography and this is the first cryptography that we have that we have spoken about. This is the symmetric key. Is that we have so it has much of theory on it. We will share these notebooks with you guys if anyone would like to go throughout it by himself. He is fine to do that. But I'm gonna go through it very fast because we cannot read all of the information here. So I will just give an overview about it. But the first thing that speak about the symmetric key is that we have what I have shown previously, that we have the secret key, or called the symmetric key, that both of the parties, that Alice and Bob, they maintain the same key, and we use it for the encryption and the decryption. And this key should be kept safe, because if anyone put his hands on this key, for sure he will be doing the decryption or know what we are sharing. So so we have many algorithms that work in this. This is an example of them.
Sorry, I think the screen you share is different from here.
Okay. Yeah, stop the sharing.
Yeah. Mm.
No, no.
Oh, yeah.
Right now you can't see my screen, right?
Oh, this is the screen which is being shared.
Yes. This is
This is the screen. Control it here.
right screen.
Okay.
So this here, yeah. Check it here and then.
Okay. So sounds good. We have that much of stuff. So this is what called the symmetric key cryptography, and we have all of these algorithms, and each of it has been built on a different mathematical problem or way to program to write the algorithm. So all of these algorithms cannot be counted as 100% secure. But we rely on them for our encryption and decryption, because no one has proved that we can break them until now. So we are still using them, but these cryptographic algorithms are not totally 100% secure. So after that, we have the public key cryptography. Is that this is the one that we have shown that it has the private key and public key. So each party or each one of the communication party, it's either Alice or Bob. It has its own public key and private key, and we use them. They use the public key for the encryption of the data, and the private key is kept safe. That's the one is used for the decryption. So why we need the public key cryptography? Does anyone know what the public key cryptography, like why do we need them? Like, what they solve for us? What advantage above the simplicity? Can anyone guess? Even like give a guess? Yeah, we need. Yeah, it could be. Yes, it could be like the answer. So the simplicity, both approaches they can generate the simplicity, but how they portray it through the internet. So without like any like previous communication or like they have initiated any key, they will not be able to share the key. So we have the public key is overcome the attack problem is that when we distribute the key, we are using the public key to give our keys and then we send them. And the private key gets saved, which is will be used for the decryption. So so then after that, we have the hyper system. The hyper system is the one that we are using right now. We are using the public key, cryptography, the private and the symmetric cryptography, both of them in our communication. So, for example, when you send a request to the server, that the very thing that what happens, the handshake, which both of the parties they exchange the public keys, and then after that they come to say that both of them they generate their own symmetric key and they exchange them with each other using the public key. Because I have the public key of the other party, or like imagine that I'm Alice, I have the public key of Bob. I can generate the key and send it over to Alice, because I only she's the only one has the private key. She will know the symmetric key I'm sharing, and then after that we can initiate our like communication using the symmetric key that has been shared. Thank you so much, man. That was such a fun.
Yes, I think I should receive an outstanding
Yeah, for the right. Okay. So so this is a hybrid system. Actually, we have this like we have this table. It shows that we can use less number of bits on the symmetric keys. Is less than in the RSA and the ECC key state, which is public key cryptographic system. So why do we have a less number of bits in like getting the same level of security or getting the rate? This is because of the algorithm that that each cryptographic algorithm rely on, or the main base concept behind it. So here we need much more longer bits or keys to achieve the same level of security that in the symmetric key that only like 80 bits can achieve. So this is a very simple thing. So the quantum, so and then we have the quantum cryptography is just saying is that why we do need them, because of the threats that's going to be happening in the future. We have the short algorithm. It's listed here is that it can solve the problem in log-in of time to break our keys. So that's all. So mainly if we see the quantum computers, that is would be like part of the life. So it would be a cyber that knowing communication will be secure. If I know your public key, I know your private key, I can encrypt the data and get all of them. So that's the people like went to the quantum area. We have the non-cloning theorem, and this is a small proof of it. If anyone would like to go through it, because I don't want to waste the time on it, but it's very clear for anyone who would like to go through it. Imagine that we would like to clone the Thai state. This is like an example here. This is a clone operation, and we will generate the two states. And from here, the last thing is that from our proof that both of them does not. The main thing is that we will not be able to clone a state in a support position, because we will not be able to know the coefficient that we have. There's no any operation that can clone the coefficient for of our superposition. So I would like to go back to I don't think you guys can see my screen. I think. Could be fine. Got it. Well, sorry guys for like slowing for like having this many stops in the presentation, but actually I think I'm frozen here. I'm not able to show my slides.
Yes, should bring the mouse to here.
Yes, I am.
Wait, this mouse. Yes, okay. So place the big one. Here you can see. Okay, you have to get the mouse.
Yeah.
Okay. All right.
Sounds good, sir. No. So, basis of the quantum. So, if you would like to initiate quantum key distribution protocols, for sure we have different phases. We would like to go throughout them to run our QKD protocol. So, it's very common stages between the protocols. So, imagine that we have the first phase that we will start from is the qubit exchange phase. So if I would like to initiate the symmetric key using the quantum key distribution, the first stage is the qubit exchange phase. So the sender sends the qubits to the receiver in this phase. This is the first phase. The second phase is the key shifting. So the key shifting is the sender and the receiver to exchange their use bases, and they only keep the bits according to protocol shifting algorithm. So both of the parties, they exchange the qubits, and then they would go to the second stage, which they do the key shifting, which they keep only the bits that they will save for the final key. And then they would go in another phase, which is called the eavesdropping testing. So in the eavesdropping testing, it refers to the process of detecting the unauthorized listening or the interception of the information. So after they complete the second step, they would go in like testing if there was an eavesdropping happen in the middle or not. And this happened by choosing random bits to do the testing if they see if they have a matching result or not. And after that, we have the error correction phase, which correct the bits. So after doing the eavesdropping, we have two options. Either we abort the protocol if there was much of errors or more much of flipped bits. That means that there was someone in the middle who did who was trying to do an eavesdropping. That means we will abort the protocol and we will start again from the beginning. But if we pass this phase and everything went fine, that means we will go to the next step, which is the error correction phase. As we know that when the qubit travels from one side to another side, there is much of noise that the qubit will be affected by this noise, and sometimes we will get the qubit will be flipped. And to get the same symmetry key like for both of the parties, we need to run a correction algorithm. So this mainly algorithms will go to make sure that Alice and Bob, they have the same key. And lastly, we will go to the privacy amplification phase, which this process tries um, to inspect or see how much information the eavesdropper was able to get, and it will try to minimize as much information that is was able to get by dropping those bits.
Big question. Can you go to the next slide? So it's the average swapping might change the state of the quantum qubit.
Yeah, so imagine that Alex sent the one, but Bob, he will receive a zero. And everything, they use the same case or the same the sifting process like as went through, like everything was fine. That we need to sift this key because we have a multiple key. And lastly, what Alice had said would be one, but Bob got a zero. And that would happen because when the qubit is traveling from in the fiber optic link, it would be because of the noise. Because the qubits could be affected by any noise in the channel.
Yes, I know it's about by the I'm asking the if this average dropping, somebody just intercept your the receiver.
Okay, if you're asking about the eavesdropping state, if that's the eavesdropper, he will intercept the qubit and do his measurement, and he will change the qubit.
He will change it.
Yeah, the final bit he will change. Yes, the state will be changed. That means when Bob he will do his measurement, he will get another result.
Okay.
And from that we will get. So we will go through all of this stuff, but this is mainly the common phase of the quantum key distribution protocols. But we will see them. We will dive into our first protocol, the BBS protocol. All of this stuff gonna be very clear. So the communication channels. So when we are speaking about the quantum key distribution, that does not mean that we will go all of our communication going to go into quantum channel. We will have the classical channel and the quantum channel. So the quantum channel is used to exchange the qubits between the sender and the receiver. It could be a fiber optic or a link or a free space. So basically, we're going to initiate a quantum channel in plus to the classical channel that we have. Because the quantum like key distribution is only for initiating the key. And then we will revert back to use our classical channel to do the communication. So we have quantum channel and the classical channel. The classical channel is the normal channel available between the sender and the receiver, which Alice and Bob used. So the main thing why we will need the classical channel, because we can exchange the bases and performing the error correction. So we will need this classical channel to do that. And the classical channel would be the internet or what we have like normal right now. So to our first protocol, the BBA4 protocol, QKD protocol. So this is one of the first QKD protocols. It's invented by those two scientists, Charles Bennett and Jalos Prasad in 1984. And from that, the name of the protocol comes, the BBA4 protocol, from the inventors and the year. So this protocol was made to enable two parties to securely exchange the keys using the principle of quantum mechanics. The BBA4 protocol has two communication channels. So every protocol is different. Not all of the QKD protocol are very similar. Some of them have the combination of the quantum channel and the classical channel, and some others like go only on the quantum channel. So every protocol is different from the other protocols. So we have the quantum channel for transmitting the encoded photons, and we have the classical channel for sending the measurement-based information and ensuring the secure communication. So what will happen in this protocol is that the sender randomly assign each qubit to be in the state 0 or 1 based on randomly chosen basis. So bases and the states in the BPS4 protocol. The BPS4 protocol utilizes two bases to generate the polarized qubits, which what we call the rectilinear base and the diagonal base, which those are the two bases. We can call them the plus base and the X base. So this how the rectilinear base would look like, and this is the diagonal base. So the diagonal base is like 45 and 135 degrees, and the rectilinear is is the horizontal and the vertical axis. So both of the states 0 and 1 could be generated by using the two bases. So by using the plus base, we can generate the 0 state and the 1 state, and also by using the X base. So for simplicity, guys, we can just call it the polarization of the photon. So imagine that I'm sending a qubit in the zero in the plus base, that would be a 0 degree photon. And if I'm sending a 0 in the X base, that would be a 45 degree. And if I'm sending a qubit in the 1 in the plus base, that would be a 90 degree, and in the 35 degree for the X base. So it's simply like not 90 degree one. So the rectilinear, this shape, it has a 0 polarized photon and the 90 degree. Yeah. So if I'm sending a 0 in the plus base, that means I will send a photon polarized at the 0 degree. If I'm sending a 1 in the plus base, that would be a 90 degree. If I'm sending a 0 in the X base, that would be a 45. If I'm sending a 1 in the X base, that would be 135 degree. I hope that will be very clear because we will use them in our. So this would how would the BBA4 protocol will look like. We have the quantum kernel and we have the public kernel. So the quantum kernel is used only to generate the key, and then after that we can use the generated key in our public secure kernel, which we will use it to send the messages. Yes. So the quantum kernel and the classical kernel, we will use them to generate our symmetric key, and then the communication kernel, we will use normal communication kernel for the classical kernel, because we will use only the quantum kernel for the EPA to initiate the symmetric key, and then we will revert back to our normal communication method, which is the classical kernel, and we will use the symmetric key generated to encrypt our data. So this would be a very simple example about how we will go through how Alice would share a symmetric key with Bob. So this example. So imagine that we have Alice. She gonna generate a random bit, and she would like to initiate the key from this bit. Or share these bits with Bob. So Alice would also generate a random basis, and then after that we will generate the qubit or the polarized photon from this, and this is shown for the simplicity about how the qubits. So a 0 in the plus base, that would be a 0 degree photon. The 1 in the plus base, that would be a 90 degree, and etc. That's what we were speaking about. So, and then she would share these qubits with Bob, Bob, he will go and use a random, he will decide randomly which basis he will use for each qubit to do his measurement, and then he will do his measurement on that. So the BBS4 protocol, the main thing about it, if Alice and Bob they use the same base, that means for sure Alice and Bob they will see the same result. So if Alice sending a 0, Bob he will get a 0. If Alice sending a 1, Bob he will get 1. It's only relying on that both of us we are using the same base. But if they are using a mismatching base, that means we will not include this bit in the final key. So from here, this is the generated key, and we will go throughout it because in all of these cases, they have used a matching basis. That means they will generate bits from that. And for all of these other cases, which in this case, Alice, she sent the one to the plus base, and Bob has used the X base. That means they will not get a matching. They will not get a matching result. So here comes the thing is that when they use the matching basis, we have 50% that either Bob will get the correct result, or he will get the mismatch result. And that comes from the qubit that when we send it, we have a superposition. Is that the qubit decides to collapse in which state it depends randomly and rely on the qubit itself. So in a mismatching base, either we will get the correct result, either we will get the 1 or 0, and for that we will not include it in our final result. So all of these cases, it has a mismatching basis. They have used mismatching basis. That means we will not include them, even if Alice got the same result. So drawbacks of in the BBS4 protocol. So the BBS4 protocol is sensitive to noise in the communication channel, which can introduce errors and reduce the key generation. So the BBS4 protocol is really sensitive to the noise. I believe all of the quantum kits also have this sensitivity, but I think BBS4 protocol has the most sensitivity here. The distance limitation, we have this problem in much of and all of the QKD protocol. So the effective transmission distance is limited due to the attenuation and the loss of the photons over the long distance. So when we are sending photons for a long distance, sometimes we would lose them, or sometimes they would be flipped because of the noise. Also, one of the main things is that the vulnerability to the photon splitting attack. So this one of the main attacks that could happen in the BBS protocol is that when we have these lasers that generate for us a qubit, those lasers are not efficient in a way that when we would like to send a qubit, it would not generate only one qubit. Sometimes it generates many qubits. Yes. And what the eavesdropper gonna do, he will be in the middle, counting the number of the qubits. If he finds more than 2 qubits, that means I will keep a qubit for myself without doing acknowledgement or anything, and I will forward the other qubit to the other side or the wall. And then when both of them are doing the base XK, like in the base of the base XK, I can know which bases they have used for to encode the qubits, and I can get the key. So this is one of the attacks. So I think what the people are doing right now, they are trying to improve the lasers to make them perfectly efficient in generating the qubits. In fact, when we are just sending one qubit, that means that we are only sending the qubit. That's one. So we do have a notebook that go throughout the QKD. This is I think everyone can open it in his laptop, and it's called with us, always up, to see how the BBS protocol works. If man can share So can you all see my screen? Okay. Good. So for this notebook, we have some of the theory, like the background of the BBS4 protocol, all of this stuff. So because we have very limited time, so I'll leave it for all of you guys. But it's simple, it's speaking about the basis, how we can, what are the qubits are encoded in vectors, the zeros in how the qubits are encoded in vectors. It's very simple for you guys to get it. The key exchange first. The key shifting, that's what we spoke about. If we have a matching basis, that means we will keep the key. If we have a mismatching base, that means we will neglect this or ignore this bit, or qubit that has been exchanged. So the eavesdropping detection, that's what I did not speak about. So after doing the key shifting, that's what we have spoken about, the basis of the QKD protocol. We would come to the eavesdropping detection. So in this phase, what Alice and Bob they would do is that they would choose randomly between the secret key or the secret key that they had. They're gonna split it in half and use it so bits for testing the eavesdropping. And how they would test the eavesdropping is that they gonna check, because we have used a matching base, that means we have the same bits. So they gonna disclose the bits that I've mentioned. So if they found much of this matching has happened, that means an eavesdropping was happening, and we need to abort the protocol. So yeah. So we have a very nice simulation here for you guys. Unfortunately for you guys, if you guys are on Colab, you guys will not be able to run this simulation because I'm running it here on my PC on Anaconda. So I will be the only one who will be able to run here, but I will show it to you guys. So this is what Alice she's trying to send to Bob, and this is the base also like has chosen randomly. And this is the polarization, the generated qubits, what we call the generated qubits. Those are the bases that what he will use for the measurement for each qubit, and this is the measurement outcome. So here we have three options. It's either 0 or 1 or unknown. So for the first one, what do you guys think here? Would it be 1 or 0 or question mark? We would go with that. Okay. Okay. For this one, we have 1 encoded in the plus bit. That's mean a 90-degree, and Bob has used the the X space. What would be the result here? Any guesses? Anyone welcome to help me, guys? I'm not able to help. Okay. What's for the third word? I think it would be a question mark also. Okay. Okay, question mark. I don't know why. What would be here the result? Okay. Okay. Question mark. So let's go to check down. All of them are correct. Ooh, you guys did it. Yeah, you guys did it. That's very bad for the cost. So I hope everyone here got an understanding of how did we get all of these values. All of us are good. All of us are the same page. Good. So we have this code. Unfortunately, this code is not built on Kikiskit. You guys can go after that to change it to Kikiskit, but that's the simulation that we will show is that it's built on Python code, but we will show a simulation how the BBS4 protocol works from the beginning until the last stage. So this would be a widget that, so all of you guys, if you guys are running on Colab, from here you guys should be okay. you guys will be able to run all of this code. So you can play with the code, change the variables here as much as you can, and you can see further on. So we have, okay. This is a final key. Okay. So here you would be able to enter the number of the bits or the number of the bits you would like to exchange with Bob. And here from this option, if you would like to activate if or not. And we have in the BBS protocol, we have two bases. It's either the diagonal or the Z base or the rectilinear or the diagonal base. So also we can enter the percentage of the which the diagonal over the standard base. From here we have we are initiating a class that has all of the methods that we will use in our communication in our code here. So it starts from here. It displays to you what variables did you have here. So basically, you would like to initiate 100 qubits. You would like to send them to Bob. In this first time we will run the code, we will count that if we will not intercept the transmission. Alice has a 50% of chance of choosing the diagonal base over the standard base, also for Bob and Alice. So the code starts from here is that we would ask the code to generate bits randomly and also generate the bases randomly, and this is going to be shown to us here. So we have this table show to us we have generated is one in the plus base, that's mean a 90-degree, also one, and we have 0 the plus B in the plus base, that's mean 0-degree, and one in the X base, that's 135 degree. So now we know what Alice would like to share with Bob. In the other side, we have Bob. We will ask him to generate the basis, a random basis, and then he will receive the key. So the receive key is a function that what will do for us the key shifting, the measurement and the key shifting will happen in this function. So what we will see is the result. So this is what Bob has chosen from the base, and this is what his observation, and this is his translation of the bit. So 45 degree, 45 in the X base, that means 0, plus in the, and he observed a 90-degree, and he's using the plus base, that's mean 1. That's from what we have shown previously. From that, they're gonna go to do the comparison of the bases here, and they will show the keys. So here we have when they have used a mismatching, that would put W, which is wrong, for a matching case, that means C, which is correct, and they would generate the secret key. That means Alice sent me a 1 and I got the 1. But for all of the cases that we use the mismatching basis, we will ignore them because they have the wrong or mismatching base. From here, the last. That this code like do the half. So the code like what it does is that it goes to choose randomly from the secret key and do the comparison of the keys. So Alice is doing check on the keys with what Bob will share with her. From he will send her the values that she needs to check and the bits to compare, like the position of them, and the basis comparison that the basis key has used. The result of the basis comparison, that's both the correct and the wrong. And lastly, we will show the key is that, so all of the cross bases here, I think those are used for the testing. So all of the bits or the qubits, we will use them to do the testing, we will exclude them from the final. So if we have used any bit for the testing of the dropping, for sure we will not include it in our final key. So all of the ones that has the check marks, that means we have used it to do the testing for the if dropping, and we will not include it. And this will be our final key. And the coach shows to you like everything seems okay. No, if dropping has been taken and comes off. So let's go and run the code again. In this case, Eve will be in the middle and she will try to choose randomly between the bases, and she will conduct a measurement, and she will either get the correct value or she will flip the value for us. Now the tables will be different, I think, for the next. So if you guys, so here we have Eve's base, and that's what she observed, and she will translate it to 0. So she will send like a 0 to Bob in a qubit that is encoded in a 45 degree, and Bob if he use the same base as Eve's, he will get the same result. But the thing is that when Eve's in the middle, sometimes she will get some of the values or the qubits. She will do the measurement in a correct base, and sometimes she will use a mismatching base. And from that, she will flip the values, and we can detect that when we come to the like the eavesdropping testing test. If you guys look, okay, I think I missed one of the. So this is a mismatching of the. It seems that there's has been an eavesdropping, and this happened from the eavesdropping testing phase that we discovered that we have many of mismatching cases, and from that we will abort the protocol and we will start again from the beginning. So that's all. If you guys want to play with the code, you know, work. So I think that's all right now for me. I will hand it over to Mandy. She will speak to you guys about the B92 protocol.
So now I'm gonna go through two other protocols. So before that, let me ask you a question. Is it too much for you? Is it like too much information to take in, or are you guys doing good? Good. Okay, let me introduce myself. I'm Amin, and I'm doing my master's majoring in computer science here at UTC. So, okay, I have one more question for you. Do you want me to explain a simple protocol or a bit more complex than the simpler one? It's up to you.
Would like to learn the most complicated.
Okay.
That, yes, things like that. But I'm not sure that I can understand.
That's a good answer. Okay. Based on the time constraint, I'd go with a simpler one for now. We can just cover the next one in the next session. Give me a minute. Is it okay in the Zoom, Dr. Liang? Is it okay in the Zoom? Is it the same slide which is showing?
You want to?
Yes, okay, thank you. So this protocol is called three stages protocol, and it is developed by a person called Subhash Kak in the year of 2005. This protocol is also called Kak's protocol or ping pong protocol. You'll see why it is called ping pong protocol based on the procedure, like how the qubits are transmitted. So the difference between other QKD protocols and this protocol is just that in other protocols, qubits are transmitted only in one direction. But then in this, the qubits are transmitted bidirectionally. That is, Alex sends her qubits, and again Bob sends his qubits back to Alice. So that's how it is bidirectional transmission. And also in this, there is a concept called transformation matrices, which is applied both at Alice's and Bob's end to the qubits. You'll understand this later when I go in detail to the procedure. So we'll choose a state among one of the two orthogonal states. The fundamental value should be 0 and 1 because it is easier to explain and it is easier for the beginners to understand how the protocol works. So basically the second equation is the one which you are seeing. That's basically the general notation of how two orthogonal states represent. You can just plug in any values of alpha and beta, and yeah, you'll have two orthogonal states in your hand. So as I mentioned, we have two transformations for Alice and one for Bob. What do you think U represents in that UA and UB? I told it's a matrix, transformation matrix. What does U represent in the matrix? Sorry? Yeah, that's right. It's unitary. It basically means the magnitude of the matrix is 1. The unitary matrices are used for the transformation matrix. And there's also a concept called Hermitian conjugate. Have you guys heard about adjoint operation in a matrix? Yes. So what's it about? It's basically performing two operations on a matrix, that is conjugate operation and transpose operation on a matrix. So that's basically is it annoying you? So it's basically applying two operations on a matrix, that is conjugate and transpose. There's also this rule where when you multiply the matrix and with the adjoint matrix, you'll get an identity matrix. Are you guys with me? Great. So a general notation of transformation matrix is this, which is R of theta. Alice would be using R of theta and Bob would be using R of phi, wherein the matrix's components are like this: cos theta minus sin theta, and cos theta. When Bob has to use it, he'll just plug in phi instead of theta. This is basically a rotation operator which is used to manipulate the qubits. That's basically the reason we are manipulating is when we are transmitting over a public channel, this operator makes the information secure, makes the qubit secure from the eavesdropper. So the protocol, this would be the protocol procedure. So we have a state X, and at Alice's end, she would apply the transformation matrix, and the output would be UA of X. The transformation is applied on the qubit. Now that is being transmitted to Bob, and Bob has his own transformation matrix, correct? So he would apply his own transformation matrix on the received information, and then he would get UA UB of X. And again, he would transmit it to Alice. Now, in this step, Alice would apply the adjoint operation on her own transformation matrix. That's basically a conjugate and transpose. So, what do you think the output is? I've shown it already, but I'm just asking you. What do you guys think the output or the value which Alice is sending? The conjugate, when you apply a conjugate and transpose on a matrix, it just cancels out the matrix value, right? So it's an identity matrix you'll get. So when UA and UA transpose with the conjugate, when they are multiplied, you'll get an identity matrix. So just that you'll get UB of X. Now this information is transmitted to Bob. Now Bob again, he applies his adjoint operation on his matrix, and then he'll receive the qubit. So that's why the qubits have been transmitted bidirectionally. So that's why it's called ping pong protocol. And if you observe, there are like 3 steps to it. The transmission is done in 3 steps, and that's one of the reasons it's called 3 stages protocol. Are you guys doing good now? Having? Yeah, I mean, it's not about acknowledging, it's just, this step is just basically to transmit the information from Alice to Bob. This is done in over a public channel. So in order to protect it from eavesdropping, they would just apply their own transmission matrix on it. So it's basically, this is how the protocol works. So, okay. The detection methods, this is basically to check whether any eavesdropping happened in between the transmission or not. So there are 2 methods in this. First is we'll just append parity bits. Parity bits are nothing but few additional bits which are added to the qubits, to the actual information. And after the transmission is completed, you'll just have the original information with the qubits, with the additional bits, correct? So in order to verify whether the original information, whether the information which they want is corrected, is transmitted correctly or not, they'll check the parity bits if the sequence and everything is right. So this is one method where they append parity bits, and the second one is they just append chosen bit sequences. Like they before the protocol starts, they agree upon few addresses like a sender address, receiver address, and any other hashed value. They know the sender address and receiver address, so those qubits will be appended to the actual information, and then that would be transmitted. So again, at the end of the protocol, they would just check that sequence if it is completely true. Else, if it is tampered, again they would start the protocol again.
I ask a question.
Sure.
If you go back to the free phase.
Mm-hmm.
So the reason you want to apply some kind of transformation, unitary transformation, you want to stop somebody to intercept your message.
Right.
Okay, so like for example, like the UAX UA, it can be it's a transformed message.
Yeah, it's just you just pick any value for the rotation. That is the matrix which I've shown earlier.
It's kind of linear transformation. For the hacker, maybe it's easy to. It's much become much easier to just decipher those messages. That's my question is.
It depends on it depends on the value which they choose. It depends on the theta. The eavesdropper doesn't know what rotation Alice's have, right? What value of theta or what value of phi the Alice or Bob have. The eavesdropper don't have the knowledge about that. So it's just random.
So when you means the rotation is kind of it's kind of key.
Yeah, it totally depends on the rotation operator. So that's the beauty of quantum. So you'll have the chance to pick the values randomly, whether it is basis in BDA4 protocol or the rotation operator here in this protocol. It's just like so random and so uncertain, and that provides security for these protocols. Did I answer your question?
Yeah. So you mean the rotation angle is randomly?
Yes, the rotation angle is random.
Okay. Okay. We did not hear your speech. You share your this code, Google code.
Yeah, I'll do
Why also my picture? Yeah.
it. It's just been okay. I think I hope it's good now. Sorry guys for all this messiness. So this is basically a Python code which we have written. It's basically the simulator for 3-stage protocol. So the first part of the code, it basically has, or it takes the input from the user on which basis I want to choose, which angles of rotation, or which basis I want to give, whether it is 0, 90, or minus 45, minus 45, and 30, 120. You also have an option to choose your own custom basis, but just remember that the angles should be orthogonal. The difference in between the angles should be 90 degrees. So let me run the code. Do you have any problem in accessing the code? Okay.
So we can run this code, right?
Yes, you can.
Okay.
So here, let me choose a preset basis as an option 1. And it asks me 3 options. It has always 3 options. I'm going to choose one again randomly. And I'm going to give the binary string, like some random string. So that's the first part of the code where it takes values from the input. And did you see the prompt which is asking me Alice's secret rotation? So this is where the uncertainty is. So I'm just going to give a random value here. This is theta, by the way. So this is 30. I'm just going to give her any random 50. So are you able to see the messages here? All these messages are basically for all the qubits which I'm transmitting, which I've given a value right now. So let's go through the code and then check the output. So firstly, what would be the first step, like after selecting the base? To choose the rotation and to form the transformation matrix, correct? So I've given the rotation as 30 and 50 just randomly. And then here you are able to see the unitary matrix. This function is basically to generate the transformation matrix for Alice and Bob both. So in these 2 lines, the function is being called, and then this is basically the cos theta minus sin theta, and cos theta, the transformation matrix which we have seen earlier. So the next step would be, if we go to the main function here, it's just like a for loop, and inside it has a function which is senbit. So let's go to the function senbit. So we have our own qubits, right? That is which Alice wants to send it to Bob. So it gonna loop it over the qubits. Only one qubit is taken into consideration in this function, and then that bit value is given here. And this is basically a rule to convert the bit into an vector notation, because we can only apply the transformation matrix on the vector notation, right? So it's just basically converting into an array, and this is basically the fixed formula to convert it. So after we get the desired notation, we have a function called Alice1. And in this, the inputs for this function would be the transformation matrix of Alice, that is a secret dot, and the converted vector for that particular bit. So I'm going to Alice1 function, and this returns the dot product of the matrix, of the transformation matrix and the vector notation. Are you guys with me? So that's the first step, and again that is being sent to Bob, and now Bob applies his own transformation matrix, which is this function Bob1. It's basically the dot product between the received data, received information with his own transformation matrix. And similarly, Alice2 is a function where she applies the conjugate transpose operations on the received bit, and again, she's going to transmit it to Bob. So that's the function Bob2. And now let's see the output. So I'm sending a 1 first, and the 1 is being converted into this vector notation. And now applying secret rotation for Alice. After applying it, this is the value which is sent to Bob after applying the transformation matrix. And again, Bob's gonna apply his own transformation matrix, and again, Alice gonna apply the adjoint operation. So finally, you'll be able to see the received bit after Bob's measurement is 1. This cursor is weird. Yeah. So this is just for 1 qubit. So if you just scroll down, and this is for all the qubits. I've given such a long sequence, sorry for that. So this is basically the information for all the qubits. Yes? Yes. Do you remember the values that we had while selecting the base? Yeah. So it just loops over that sequence which I sent, like which I've given. So one bit is taken into consideration, and then that's how the function is applied. So you can try with your own random values and check, and just ask questions if you have any. I think it's time for break now. So is it that way? Like, let's continue after the break. Am I audible now? Okay, I think it should be good now. Sorry for that. So yeah. So after the transmission is done, Bob would share his basis to Alice, correct? Whether the bits are matching or not. But here there is no such concept of key shifting. It's just that he directly shares the qubits which he received to Alice, and then that's how they check for eavesdropping. So as I told, the bases here used are rectilinear and diagonal. It's just two distinct states, that is 0 and 1. So coming to the protocol procedure, the first step would be Alice generating a random sequence of bits to be transmitted to Bob. And this happens over the quantum channel, correct? And now Bob, he chooses randomly between the two bases, whether it is rectilinear or whether it is diagonal. Based on choosing the base, he would get a different result. So let's see how he measures the photon. So as I told earlier, there are two scenarios here. One is Alice sending a 0 and the other is Alice sending a 1. When Alice is sending a 0, that is at 0-degree polarization state, and Bob is using a rectilinear base. So now the bases are matching, correct? Rectilinear base has both angles, 0 and 90 degrees. It's just like a plus sign. So Alice is sending a 0 qubit with 0 degrees, and Bob is using a rectilinear base. Rectilinear base basically has two angles, 0 degrees and 90 degrees. Now, the bases are matching, correct? Forget about the rules which we have used in BB84 protocol. Here, the recipe is completely different. When the bases are matching, we know that the Bob would measure a value of 0, the one which Alice is sending. The probability of getting a 0 is 100% here. We know that it's 100%, but then Bob is unsure if he is using the right base, because he expects this value 0, or in the other case, it can be 1. He expects this value, but then he's unsure if he is using the right base or not. So he doesn't detect any photon here because he's not sure whether he's using the right base. So that's scenario 1. And when Alice is sending a 0, there's another combination of Bob measuring it using diagonal basis, correct? Which is 45 degrees and 135 degrees. So now the bases are not matching. This is a part of rectilinear base, and this is a diagonal base. As the bases are not matching, when Alice is sending a 0 and when Bob is using 45 degrees angle, the bases are not matching. So the probability of getting a 0 would be 50%, correct? Because the bases are not matching. And even similarly, the probability of getting a 1 would be 50%. When there's also a sub scenario here saying when Alice is sending a 0 and Bob is using an angle of 135 degrees, Bob knows for sure that Alice doesn't have a 135-degree angle, because Alice, she just has these two angles, that is 0 degrees and 45 degrees. Correct? She doesn't have 90 or 135. She doesn't have this. She just has two angles, that is 0 and 45. Anything wrong?
The camera, yes.
So yeah, they are at 135 degrees. Now Bob is using an angle of 135 degrees, and he knows that Alice doesn't have this 135-degree angle, and he knows that he shouldn't use this base because Alice doesn't send a value at an angle of 135. So he knows that he's using a wrong base, and he'll get a value of 0, because
Yes. It's not camera. No, no, it's the wrong camera. No, because you connect with this. Yes. Oh, no, we can't. No, we can show the bar on this on the Zoom. Sorry for that.
Maybe I can just use
Because it's used the laptop camera, so I don't think it's you can see the screen. You can see the bar on that.
Okay, I can do it on whiteboard. So yeah, thank you. So, are you guys with me on this? So basically, there are two scenarios here. One is Alice sending a 0, and 2, Alice sending a 1. This is at Alice end. It's so hard to write. Sorry, guys. So Alice has only two polarizing states, that is at an angle of 0 and at an angle of 45 degrees. Okay. And again, when Alice is sending a 0, Bob has two options to choose from his base, correct? Whether it is rectilinear or whether it is diagonal. And rectilinear has 0 and 90, and diagonal has 45 and 135 degrees. When Alice is sending a 0 and Bob is using a rectilinear base, the bases are matching, correct? We know that when the bases are matching, we know for sure that it's for 100% that Bob will get a 0. But then he is not sure. He needs some confirmation whether the value which he is receiving is appropriate or correct or not, correct? So he's unsure of whether he's using the wrong base. As he's in doubt, he doesn't detect a photon here. This is basically the output. This is the output of what he is measuring. And when Alice is sending a 0 and Bob is using a diagonal base, that is 45 degrees and 135 degree angle. Now, in this, we again have like two sub scenarios. When Bob is using 45 degree angle to measure, as these are unmatching bases, we have two sub scenarios. Okay. When Bob is using a 45 degree angle, the bases are not matching. So he has 50% chance, that is, there is 0.5 probability that he's gonna get a 0, and there is 0.5 probability that he's gonna get a 1. So that's with the 45 degree angle. So again, there is a superposition happening, correct? So again, in this case, he doesn't detect a photon. It's just a question mark. The photon is basically the qubit information which you are passing. And when Bob is measuring at an angle of 135 degrees, he knows that Alice doesn't have this 135 degree angle, because Alice just has 0 and 45, which I'm just showing it on the top above there. So at 135 degree angle, he would measure a photon with a value of 1, because Bob knows that Alice don't have this 135 degree angle, and he knows for sure that he's using the wrong base. So he gets the value of 1 of the rectilinear value. Sorry, guys. The diagonal basis value is basically 1, correct? So here I wrote it wrong. This should be 0. And the value we'd get is 0 because the value opposite to the diagonal basis value is the rectilinear base value, and he would detect a 0 in this case. Sorry for the confusion. Are you guys with me? Okay. So in the second case scenario, Alice would send a 1 that is at an angle of 45 degrees. And again, in this case, the combination of bases happen again. Bob is using a rectilinear and diagonal. And now when he's using, let's go with the diagonal first. So now I'm going to ask you questions. You have to respond to it. Let's go to the diagonal first. The bases are matching here. Is that right? Alice is sending a 1 and Bob is using a diagonal base. The bases are matching. This is my statement. Do you guys agree on it? If one of the base, it overlaps in the base which Bob has, then it's considered the bases are matching. So because Alice is sending at an angle of 45 degrees and Bob has 45 and 135. So if one of the thing is overlapping, correct, there's an intersection between both of the angles. So the bases are matching here. So my statement is correct. In this scenario, again, he's not sure if he's using the right base. It's just that we know when the bases are matching, he would get a value, but he is not sure whether he's using the right base to measure the qubit. So he doesn't detect a photon here. It's just a question. It's so messy. I can just show you a slide after this explanation. That would be like so clear for you guys. So in the second case scenario, when Bob is using a rectilinear base, when Alice is sending a 1. In this, again, there are two sub-scenarios when Bob is measuring at an angle of 0 degrees and Bob is measuring at an angle of 90 degrees. So when Bob is measuring at an angle of 90 degrees, he knows that Alice doesn't have a 90-degree polarization state. So he knows for sure that he's not gonna that Alice is not gonna send a value with respect to 90 degrees. So he knows that he is using a wrong base. So that's when he gets a value of, I want an answer from you. He gets a value of diagonal base because the base which he is using, rectilinear base, is incorrect as per his conclusion. So he's gonna get a value of diagonal base, which is 1. The value of diagonal base here is 1, correct? At the Alice's end. Are you guys doing okay? Great. So, okay, I'm just gonna stop sharing this whiteboard. I'm gonna start sharing the screen again. Okay. This just shows the a neat visual presentation, unlike what I've done. Alice is sending a 0 and Bob is using the rectilinear. So the bases are matching here. So the question mark is basically that he doesn't detect a photon. And when Alice is sending a 0 and Bob is using diagonal bases, these are mismatching bases, correct? So there would be two scenarios in it. One is when Bob is measuring at an angle of 45, and one is when Bob is measuring at an angle of 135. So at 45, Alice has a 45. So the bases are mismatching, so he doesn't detect a photon. When he's measuring at an angle of 135, he knows that 135 angle is the wrong base. So he gets a value opposite to that diagonal base value, which is 0. So similarly, it works for 1 as well. And so I just want to show the measurement slide to you. So it just says that when the bases are matching, Bob is inconclusive of the result in the second bullet point. And when the bases are mismatching, he would detect values. I mean, he would detect a photon when Alice doesn't have that particular polarization state, whether it is 90 or whether it is 135. So that's how the measurement works at Bob's end in B92 protocol. It is like completely different to the recipe of BB84. So this is how it works. I understand it's quite confusing, so feel free to just interrupt me and ask me questions. All right. Okay. So now we are at the third step where Bob detects a photon or whether he doesn't detect a photon. So he receives a sequence which Alice is transmitting. So the next step would be verification of eavesdropping. Unlike BB84, we discussed that the transmission of bases will not happen, like the key shifting will not happen in B92. It's basically Bob and Alice, they publicly share a part of sequence just to check whether if there is any tampering of or if there is any Eve present in between. They just do it publicly over the public channel. So if the number of bits which are mismatched, which is called error, if that error crosses a tolerance value, then they would abort the protocol. They would fix on a, before starting the protocol, they would agree upon a tolerance limit. And if that crosses, if the error crosses the tolerance limit, they would just abort the protocol because they know that something is wrong in the channel, or maybe there's eavesdropping happening in the channel. Okay, I think I have a question here for you guys. I need your answer on this. So did you understand when Elharith was saying about noise in the channel? Due to noise, the qubits may flip its state. Okay, so flipping of qubits may happen in two scenarios. One is when there is noise in the channel where the information is being passed, or the second scenario is where there is eavesdropping. So how do you know that whether it is with respect to eavesdropping or whether it is with noise? How do you know the flipping or the quantum state disturbance, whether it is due to eavesdropping or noise? What do you guys think about this? Just give your opinion. It doesn't matter if it's right or wrong. Yeah. That's for 3 stages. So this B92 is only for unidirectional transmission. So that's where the tolerance value comes into picture. So the noise, it doesn't happen to the entire signal, correct? The noise, it's just like a disturbance. Suppose we have a signal wave. I'm sorry guys, I can't draw a wave in the whiteboard. So if suppose there's a wave and the noise happens only to one part of the wave, correct? At maybe at unperiodic intervals, but then when the eavesdropper, when she's trying to intercept, when she's using a mismatching base or when she's using a base which she shouldn't use, there's a chance that she might flip a value. So that's where the tolerance limit comes into picture. So that's how they understand if the error, if it crosses the tolerance limit, there's an eavesdropper in between who is trying to intercept the information. Else they would just have a key which is generated successfully. That's the symmetric key. So the next step would be error correction or privacy amplification. I'll just give a brief about it. I will not go in detail because that's not in our interest. So error correction is basically, it uses a few correction algorithms to flip the bits, which are flipped at Bob's end, maybe because of some noise or due to other factors, the bits might get flipped. So they just use this error correction algorithms to flip back the bits to the original state. Privacy amplification, it is nothing but generating a short and uniform key with more security. That's basically the word just says privacy amplification. The security is more, that's just a process which is used in as a part of B92 just to provide more security to the qubits which are transmitted. Okay, I've gone through this. Okay, so in this example, Alice has few qubits, and I think I'll ask you questions in this. When Alice has 0, what base is Alice using? Is it rectilinear or is it diagonal? Right, it's rectilinear. When it is 1, that's correct, it's diagonal. So when she has 0, the base would be plus, and when she has a 1, it would be x. So the polarization states would be at an angle of 0 and 45 because she only uses those two. And now Bob, he has this random basis generated, and he would use any polarization states among those, the base which he has. That's just like so uncertain. Bob's base and Bob's measurement is so uncertain, and it's so random. And even in the code, you'll be able to see it's generated so randomly using a choice function. That's how the security for this protocols would work.
Not different in measurement. Yeah.
No, it's like, okay, same, when both are using the same basis, in this scenario, forget about BB84. In BB84, you'll get a value of what Alice is sending. But here, he's uncertain. That's just how the protocol works. He's uncertain of whether he's using the right base or not. It's just, he's just inconclusive of what he's using. He just detects photon in this protocol. He just detects photon only in 2 cases, when he's using an angle of 90 degrees or when he's using an angle of 135, because he knows those 2 angles are not presented as the same. All right. So in the first case, again, I think I'm just reiterating myself just to make you guys clear about it. Alice is sending a 0 at an angle of 0 degrees, and Bob is measuring at an angle of 135 degrees. Would he detect a photon? The answer is yes, because he's measuring at an angle of 135 degrees, and that value is not presented at Alice's end. And he knows he shouldn't use this base, and he's using the wrong base. So he would get a value which is opposite to the value of diagonal base, which is rectilinear base. And rectilinear base is, the value is 0, 0. So the qubit value is 0. So that's how the protocol is working. And the red colored highlighted blocks are the blocks where a photon is detected. All right. Let's go to the fun part now. Let me share the link. Let me know if you're facing any access issues. Are you guys able to open the link?
Yeah.
Okay. So this is basically a B92 simulator where it shows how the bases are generated, how the bits are generated at Alice end, and how the transmission is basically working. So let's do this. Let's get into the code. So the first part of the code is, as usual, it creates widgets to take the values from the user. So this whole code is just for the getting the value from the user. I think I'm unable to edit this. Okay, let's just do with the values which are already there. So randomly, I just entered 100 qubits to be transmitted, and I didn't choose the Eve to be activated. And I just gave the number 50 for Alice's diagonal base. It's just like random. You can just try with any random values. Oh, sorry.
home screen recently. Which we used. The one.
Oh, thank you.
Stop. That's correct.
Yeah. So first part of the code is basically to get the values from the user, which is just creating widgets to enter the values such as the number of qubits to be transmitted, how many diagonal bases should Alice, Bob, and Eve has. So as I'm not activating the Eve in the first case, I think the value for this doesn't matter because the Eve is not activated. Let's go to the main program. So these are the parameter values which we get from the widgets, and whether if Eve is present or not, or whether which base is Alice using, and Bob and Eve. I think there's an access issue in
Don't skip.
oh yeah. So this first part of the main program, it just shows the summary of what we have, whether it is the number of bits or whether Eve will intercept the transmission, and how much probability does Alice have over the diagonal basis. I choose 50, so it's just 50% of rectilinear and 50% of diagonal. So that's how Bob and Eve as well. Let's just go to the next step. So the first step would be Alice generating the random sequence of bits. Let's go to the function. So the generate bits function, it basically uses a choices function which chooses between 0 and 1. And it takes an input of number of bits, which I'm just getting the value from the user, which is 100. So it returns the bits which are generated to Alice. And there is this function called transmit key. Transmit key, it has an inner function inside this, which is a function call. The encode qubit is basically, it has a list. If you can see, it has a list called vocabulary, and that's basically the states of Alice's, whether it is 0 or whether it is 45. That is basically the qubit values of 0 or 1. And if the state value, which the encode bits is getting, if it is a question mark, then again it would choose a value between 0 and 1, and then that would return the vocabulary lists value. Suppose if the state value is 0, it would return a horizontal arrow that is 0-degree polarization state, because the index of this list starts with 0, correct? In Python, the indexing starts with 0, so you'll get a 0-degree polarization state. If it is 1, you will get this 45-degree state. All good till now? All right. So the transmission is happened till now, and you'll be able to see the summary of each code like this. If you want to just execute, just feel free to go ahead and change the values. So I'm passing 100 bits, and Alice is choosing, this would be the output of the choices function, just basically 1, 0s and everything. And these are the Alice's polarization states. If she has a 1, she would get a 45-degree, and she has a 0, she would get a 0-degree. So going to the Bob's end. Now, after transmitting Alice's information to Bob, what's the first step Bob's going to do? generate the basis, right, to measure the value. So even the generate basis function, it uses a choices function inside it to just choose it randomly, where it's like so random and so uncertain that this is the beauty of this quantum. So it basically gives more security because he's unsure of what he's getting. It's just like so uncertain. So he uses a choices. Okay, sorry, this is the one. He uses a choices function, and it takes a input parameter of cumulative weights and the number of qubits. Cumulative weights is nothing but, do you remember we passed the value of 50 for the number of diagonal bases for Bob? So that's basically the cumulative base. So it says out of 100%, just choose this value, which is 50. So now Bob would have 50% of diagonal base and 50% of rectilinear base. And going to the next step, here we haven't activated the if, right? So the if loop will not be executed because this would be just 0. The value would be like take, consider, or measured as 0, and the loop will not be executed. And now Bob has a receive key function. Let's go to that call. So receive key is this. So now we have what all we have in our plate right now. We have Alice transmitting the keys, Bob generating the bases. So this receive key, it uses both of them to check whether they are matching their bases or whether the bases are mismatching. So this is basically the input of what Alice is sending. That's basically converted into a list for easier access of index. And you delete the previous iteration. The delete of self key is basically deleting the previous iteration and starting it from the start. So this if else conditions is basically if Bob has a plus, it randomly chooses again between 0 and 90 degrees. If Bob has a x, that is diagonal base, it chooses between 45 and 135 degrees. So after this if else is done, you can see the state and qubit, which is the input. The comparison is happening in this step. All right. So based on the comparison, as we have discussed earlier, you'll detect a photon in how many cases? Yeah, in 2 cases. That's when the Bob is measuring at an angle of 90 degrees and Bob is measuring at an angle of 135 degrees because those states are not present at Alice end. So he detects a photon and he gets a value of 1, and those have been appended 1 or with respect to 0. It depends on which base he's choosing here. So that's been returned to the Bobs, and again, yeah. So this is the part of this code, and you'll be able to see Bob's interpretation here. That is, if you see a question mark, it means that he didn't detect a photon. And there are values here like 1, 0 based on the base which he chose. This is basically the output. It provides a summary for each code. And the next step would be checking for E, right? So this function find questionable bits is basically it checks at what index the Bob doesn't detect a photon. So that's been stored in the questionable bits parameter. And the scratch bits, it basically discards the questionable bits. It discards the cases where Bob doesn't detect a photon. All right. So I'm just not showing it in detail because it's just back and forth and to and fro. So okay, let's go to the show valid key. Yeah, show valid key. So the do you remember the questionable bits function which we have? That finds out the questionable bits and it returns the indexes, correct? So in the next scratch bits, it discards the questionable bits and it gives a value of 1 where the value is 0 or 1. Where the value is 0 or 1 in the input. So in this function, it loops over the input which show valid key has, whether it is Alice or Bob. And if the check bit is 1, it would append the value of the key to the output. That's basically a list. Output is basically a list which is initialized here, and that output is being returned. this is being done for both Alice and Bob. All right. So you'll be able to see Alice's secret bits and Bob's secret bits. You'll not see the question marks here because it's been discarded by the scratch bits function. So you have a statement here which says the expected number of usable bits is 50 and the actual number is, what's that? 30. So we are choosing 50% of diagonal base and 50% of rectilinear base, correct? So the expected value, the fixed number would be n by 2 because there's a half percent, like that is 50% of probability of detecting a value whether it is 0 or 1 and 50% of mismatching bases. So in this scenario, it says n by 2 is 100 divided by 50 is, 100 divided by 2 is 50. So that's the expected number. But then as the bases are generated randomly, we just have a value of 30. So that's just for how many bits we detected the photon. And coming to the next step, it chooses half in the questionable bits. The questionable bits is with the one where the question marks are there, where he didn't detect a photon. It chooses half of them and it checks Alice. In the first step, Alice checks whether he transmits the valid key or not. And then it takes inputs as bits to compare is this parameter where Bob chooses half of the parameters, and then Alice checks only for those qubits which Bob is sending. And again, when Alice sends her checked bits to Bob, in this function call, now Bob checks whether they are matching or not. All right. So this is, you'll be able to see here a parameter which says switch agree. So they only choose for half of the qubits because the other half is the actual information which they shouldn't transmit. So this is basically like appending parity bits, or this is basically some additional information for which they are checking. And here you'll be able to see Alice and Bob, they are checking for 18 bits and 18 bits are matching out of all. And it says there is no eavesdropping detected because all the bits are matching. Are you guys doing good now? Okay, seems so. And out of the 30 bits, the actual number is 30, right? Out of the 30 bits, they have checked for 18 bits, and 18 bits, all of the 18 bits are matching. And there are just 12 bits which are remaining to transmit the actual information. So they're going to just use these 12 bits to send the information from Alice to Bob. So if you want 50 bits to send your information, think of how many bits at least you need, at least double of them, correct? Obviously more than double, but at least the minimum case scenario would be at least double of them. Suppose I have 50 bits to be transmitted. So I would just send 100 because there are many factors. Maybe eavesdropping might get into picture, or noise may disturb the quantum states and everything. So the key generation rate is basically how many bits, the percent of how many bits are actually being used. So in this case, they are just 12. So the percent value is 0.12. So that's all for B92. I hope you understood this. Okay, I'm just going to hand over to with the eavesdropping. Okay. Okay. So now let's check this scenario when Eve is activated. I'm just gonna run it again. Are you guys able to run the code? Okay, all right. We're just trying to experiment, just giving some random values to it. you can do that, and please feel free to ask any questions to Elharith or me. Now I've activated the Eve. I'm just gonna run the code again. So I'm not gonna go to the code again because we have seen the flow. I'm just gonna see or just discuss about the output switch for each code. So Eve is activated. And once again. So now you'll be able to see this message saying Eve will intercept the transmission because I've activated the Eve in the first step. And the value should be same 150. And now let's generate the qubits. So it doesn't make any difference here because it's at the sender end. And now as the Eve is active, now Eve present will have a value of 1, correct? Because I just toggle the button for Eve. And now you'll be able to see the values which Eve received, and she also generates, okay, when this part is being executed, she receives the qubits which Alice is transmitting, and she also generates bases because she needs to measure the value of qubit, correct? So she generates the bases and she receives the key which Alice is sending. So it's just gonna show a question mark where she's not detecting the photon, and this is basically the Eve's interpretation that's basically if it is 1 or if it is 0, or in case if it doesn't detect a photon. And from there again she's going to transmit it to Bob, and Bob is also again going to choose some random basis, and he's going to interpret with respect to Eve's transmitted value. So it's basically just replace Alice with Eve in this situation. So Eve is using a 90-degree value here, and okay, this is 90 and this is 135. And Bob is just randomly choosing a different base, and he would get value based on Eve's here, not Alice's, because Eve is in between, and he or she's gonna mess up the whole communication. And then again, the questionable bits and everything is gonna come into picture. And again, in addition to Alice's and Bob, Eve has his own interpretation, correct? Whether he detects a photon or not. So yeah, let's see the final message, what we got. So it says Alice and Bob matched only 9 bits out of 11 usable bits. So in this case, there are just 2 bits unmatching. So maybe that's the error which is crossing the tolerance limit. So it says there's an eavesdropper. So you just have to abort the protocol and just start a new one. So yeah, that's how this protocol works. I'm just gonna hand it over to Elharith for the remaining of the session. Thank you.
Okay. Can you all hear the voice? Okay. Okay. So right now we have been through many protocols. You guys would know that we have different procedure for every protocol that any of the QKD has its own procedure for P15 procedure. So all of these are very different. Yeah. So all of these are very different protocols, and each of its unique code has a different thing. So this another protocol called the Ekert protocol, E9 protocol. What is unique about this protocol is that we are relying on using the entanglement on this protocol. So this is like the uniqueness of this protocol. So Ekert is a protocol, it's a quantum key distribution protocol proposed by Ekert in 1991. It differs from the other QKD protocols because it relies on entanglement to generate the shared key. So the photons are generated by common photon source to establish a secure key between the sender and the receiver. So how the entanglement can be shared? Actually, we have a source of entangled photons. They're going to be in the middle. Alice will ask this source of photons to generate an entangled photons, and one of the entangled photons can be shared with Alice, and the other one would be shared with Bob. So both Alice and Bob are connected to a central source of entangled photons. One photon from each entangled pair is sent to Alice, and the other one is sent to Bob. So basically, here on this protocol, we are relying on the Bill's entanglement rule. Is that we are using the set rule? Is that we are generating two photons? Both of them are entangled. That means they are connected to each other. One gonna be they're gonna be in opposite direction. That means one of the photons gonna be upward, the other one gonna be downward. So the basis and the state in this protocol. So this protocol uses the Bell state to generate the entangled photons, and this is the equation of the Bell state. The third one. So one is gonna be upward or 0, and the other one gonna be 1 or 1 and 0. So the E91 quantum key distribution protocol uses two groups of bases. Actually, Alice has her own basis, and also Bob has his own basis. So Alice uses one of the three bases that she has to do the measurement. Actually, she has A1, A2, A3 because she is Alice, which correspond to the polarization that or the rotation that we can do for the qubit, which is 0, 45, 90 degrees. What Bob has is that he has his own basis, which is B1, B2, and B3, which corresponds to 45, 90, and 135. From here, you guys can see that they have two matching bases. Is that A2 is matching to B1 and A3 is matching to B2. So both Alice and Bob need to use the same photon polarization to achieve the same result. So they should agree. Okay.
It's very interesting that they mentioned that photon plays a very important role in this QAD protocol. And I remember that Dr. Tian Li mentioned that a quantum channel can be implemented by different ways, right? So that means that if we use another way to implement the quantum channel, then these protocols may not work.
Actually, can you
what do you mean by quantum channel? So I remember in your session, you mentioned that there are several ways to implement the quantum channel. So I remember you the force that you mentioned in the protocol, like that. Here we just are talking about, but if we go to other ways regarding the quantum channel,
I mean, the correlation degree of freedom,
yeah,
is that right? I mean, the entanglement degree of freedom.
yeah.
Okay. So, yeah, so the quantum channel, I didn't mention quantum channel. Well, quantum channel, in quantum mechanics, quantum channel means that the channel that you transmit 2-bit. Okay, so here, if you refer to quantum channel, that means that is whatever you use, like air or fiber, that's where the 2-bit transmit, that photon will travel in that medium. So that's the quantum channel. So here they use the basis, and this basis is based upon the entanglement degree of freedom, which is polarization, which is the electric field oscillation of the photon. So that you include in the entangled information on that degree of freedom, which which is not a channel, it's a degree of freedom. So you can entangle photons in terms of the polarization, or you can entangle two photons in terms of their energy and time, or you can even, there's angular orbital angular moments, OEM. You can entangle photons that degree of freedom. There are multiple degree of freedom you can entangle the photons.
So can I say that regardless of the implementation details of quantum channels, all of these kind of protocols should work?
As long as you have degree of freedom and you have a way of measuring that degree of freedom, yes. So now, because entanglement is coded in polarization, you have to, and polarization is related to the oscillation direction of the electric field. That's why you have to set up the degree there, 0.4590. Yeah.
So for our example here, if Alice and Bob, they would like to get a matching base, that means if Alice has used A2, the A2, Bob needs to see the B1 so that they get a matching result. So this could show a diagram that show how the E91 protocol work. Is that we have the central source. It will share one of the entangled qubits, one with Alice and one with Bob. Alice will choose randomly from her basis and conduct her measurement. After that, we have Alice. We would do the comparison of the basis. Lastly, we're gonna do the eavesdropping testing within mismatching cases, which is built on the mismatching cases. And then we have the error correlation. And lastly, we have the privacy amplification. So I want to check something like very quickly. Sorry, guys. Okay. You guys can just give me a second. Looking something. Not on the slides, but I'm opening the wrong slides, I think. Yeah. So we have this example that show how the QKD work. Okay. It's taking time because I'm uploading it from the field. So that's what we have. So Alice would so here Alice doesn't generate the random bits for us. We have the central source who generate the intangible photons. That mean he will generate using the Bell's rule. One of the qubits gonna be in 0 and the one gonna be in 1, or either 1 0, and it will be like that. Bob, he will use Alice, he will decide randomly to which base he gonna use to measure her qubit, and Bob he will choose randomly which base he will use to measure his qubit. The one has been shared with him. So it depends on the measurement. We're gonna see the keys, like where they have the matching base, as we said, the polarization. That's the one that generate for us, generate the last key. But for the one that is we like say it's mismatching polarization, like those examples, it will not generate any final result for us. And this is how the Ekert E91 protocol works. So as you guys like right now see, like it's different. Every protocol is different. We have many protocols. Those are just like a little of the protocols that we can show to you guys here. So the eavesdropping detecting. So after that, on the BB84 protocol and the E91, on the B92 protocol, we split the sifted key into 2 halves and use part of it for the key segment. But here in the E91, what we do, so I still have the same slide. I changed the slides, but
So everybody can hear you and share.
Yes.
Okay.
Oh, it's okay.
Record. This one.
Sharing, yes.
It's this one.
This one.
Okay. I'll leave the podium to you.
Oh,
You want to introduce yourself? Introduce your advisor. Where's your advisor?
Yeah,
Okay.
I'm a current master's student here in computer science, and my advisor is Professor.
Don't one of you want to stand up?
And also Professor Liang. So, yeah, now I'm gonna do the introduction to the quantum long short-term memory, which is QLSTM. And QLSTM is based on the LSTM, which is an RNN and is recurrent neural network. I think most of you guys who learn machine learning is pretty familiar with this. Now I'm gonna show an example. Like here, Tom was born in Chattanooga, and he likes playing basketball. He's very good at math, and he speaks fluent. And if we want a computer to like fill this blank, we're gonna maybe for us we're gonna say he speaks fluent English because Tom was born in Chattanooga. But like when the computer deal with this problem, and you input this sentence to the computer, and for each word is kind of a state for the computer, and he will when the computer is at this stage, the fluent, he will predict the next word. So so all these words from Tom to the fluent, all these words the computer will save it to a hidden state, which is here. We can say this is RNN, and this line is the hidden state. So it will save all this message to the network and then generate the result. But in this case, we will have a problem that there are a lot of information and the computer does not know whether which word has the most effect to the word next to the fluent. And also here we can say HT is the hidden state, and we're gonna update the hidden state each time when we typing another word. And here is the weight. For example, if the weight is less than 1, if most of weight is less than 1, when we take the gradient and we want to check whether Chattanooga has the most impact to the, sorry, I'm kind of nervous, has most influence for the English, then we will have gradient vanishing problems. So that's why we need to have long short-term memory. So long short-term memory, here is the hidden, is the cell state. And if we use LSTM, we will check whether we're gonna forget something or what thing is important, which thing is important that we need to take it every time. So let me show you. So this is the hidden cell. So this is the cell stage, and this cell stage. And first we're gonna first when we input the data X, and we're gonna I'm sorry, so nervous. Yes. Yeah, first, this is forget gate. And here we're gonna, this is called a sigmoid gate. And for this sigmoid gate, for this sigma, we can understand is the proportion that the information that we wanna transfer to another stage. And in the forget gate, this gate is for us that what thing that we need to forget. For example, we update the XT, and this is our new information, and we have some previous information in the cell state, and we do not want to remember this information, so we're gonna forget. And maybe we do not want to completely forget this information, so we only want to forget part of it. So this sigma is kind of gate to adjust what we should forget. And here is the input gate. And the input gate is because, for example, we know Tom was born in Chattanooga, and Chattanooga is a very important message. And we want our cell state to remember this, which is really important. And we want to give it a great proportion of a space that we save this message. So here is the sigmoid. This is called sigmoid function, and this is arctangent function. And arctangent function, and you may ask like why we use both sigmoid function and arctangent function, because arctangent function is like a scaling for us. For example, if we want to rate a student got 100 in his final, and we want to rate the student from 0 to 5. And so 100 is really big to fit our model. We want to scaling, like maybe we can say, okay, this student got 100, which means he got like maybe 5. We want to scaling to 0 to 5. So arctangent is scaling. The range of arctangent is from -1 to 1, and the sigmoid function is 0 to 1. And the sigmoid function, it means, as I just mentioned, is you're gonna choose the proportion of the information that we wanna pass through. So this is our new information here, and combined with the hidden state, which is similar as what we have in RNN, and then we combine this together, we choose a proportion, and then we scale the data to a manageable range, and then we input to the hidden cell. We input to the cell state. And as we have what we want to forget and what we want to input, we combine these two together, then we can update the cell state. So we have a new cell state, and we can use the new cell state to update our hidden state. So let's come back to the previous example. Now here we can say the Chattanooga has a really good, Chattanooga has really important information. So Chattanooga maybe as we train the model, Chattanooga will stay in the hidden cell and with a very large proportion maybe. And here when we want to know whether which language he's gonna speak, then the Chattanooga will affect the result. Then we can say he speaks fluent English. So that's basic structure of LSTM. And then we can update the hidden layer. And here it can be YT or HT, because for example, if a sentence right here, we just train this model and we do not need to output like he speaks fluent. When we add the speaks, we just go through. We do not need any output, but here we need to have an output. Then we will have this output. So we will use the message in the hidden state to generate the output. But if not, we do not need to do the output. And here, but LSTM is not that strong as you think. But for example, if I have this sentence, Messi will complete one trick in final. Yeah, hat trick, right? But the computer will not know Messi will a hat trick. Computer does not know this phrase. Maybe computer will know, okay, Messi is a really good football player, and maybe he was a complete football trick, but it's not right. It's hat trick. And also, John forgot his when he left today, so he's locked outside. Keys, yeah. Why you know the keys? Because we know his locked outside has kind of connection with keys. We know if he does not have key, yeah, okay, his wife.
Yes.
Yeah. Yeah, it makes sense still. So, like, how can we know this? Because we already know the scenario and all this connection, the logic, before we see this sentence. And for the model itself, this is called pre-training. And if model did not pre-train, it does not, for a sentence, if the model does not know the grammar and also he cannot understand these phrases or the logic itself, it cannot generate good result. And also there's a pretty classical topic is stock price prediction. And maybe today when you get back to home and you say, okay, I know LSTM now and I can use the historical data and to predict stock, then I will make money. But just don't waste time. You will definitely not make money. Because for the stock price, although you have a lot of data, you have a lot of numbers, but you cannot get all this information and you cannot extract the features from the stock market. So it will not predict the trend. Or you can think if you can easily use LSTM to do this, and everyone can make money easily. So yeah, that's possible. So that's why the pre-training and feature engineering is really important to LSTM. So the model itself is not that complicated, and most of the time where people are doing feature engineering and pre-training. And so I will introduce another model, transformer. Transformer is, I think most of you know this model, and this is one of the most important model in machine learning. And it's really good at capture the features and also extract informations. And the GPT is based on this model, and it's the most important part for GPT. And in this case, it can talk with us. So now let's come back to the LSTM itself. This is LSTM, as I just mentioned. This is quantum LSTM. And we can see the main difference is right here. So here is the weight, because let's get back here. So every step we have this called sigmoid function, And we're gonna use machine learning to optimize this weight, and each step it has a weight. We're gonna optimize this. That's how the classical machine learning works. And for quantum machine learning, we replace this part to VQC. And I will show, this is the VQC. For VQC here, because all these data, the XT and XE here, they're all classical data, they're not quantum data. So for this data, we just input this data to the VQC, and we use the data embedding. We transfer the basic the classical data to the quantum data, and I will show how we're gonna transfer. And then we use the variational layer to, like, we can say, to analyze, or we're gonna establish the entanglement of the quantum data, and then we can do the measurement. And for the measurement, there are several ways to do the measurement. First, we're gonna it's 3 different ways, but you can choose what you want, and we can make a projection of the qubits in a certain basis, and also we can, because the quantum data is a probability whether it's 0 or 1, so we can measure that to find, maybe to measure we got 0 or maybe we got 1, and you can say that, okay, for example, I got 60, 0 and 41 out of 100 data. So we can use this, the expectation value, which is maybe 0.4 is our output of the measurement. This is, and here is an example of VQC. First, we have the 0 state, and then we use the Hartmut gate to transfer the 0 state to the superposition. And then the data we have is the X. The X, we use X as input, and the X, we use that as an input to management the gate, that how we're gonna rotate the quantum data right here. And here is and here we can see maybe the X is 1 dimension, and here we have 4 dimension. So we have to let the data to feed the dimension right here. So maybe we're gonna use some, like, a dimensional transfer, or for example, we can use MLP. MLP is a basic neural network. I don't know whether I can draw. I forgot to. Maybe I need to draw MLP right here. So let's see.
You can use the whiteboard. Stop sharing and use the whiteboard.
How to use the whiteboard?
Stop sharing. Click stop sharing, and then go to share. Go to share. Yeah, and then go to advanced. Documents.
Documents?
Yeah.
Oh, okay.
Sorry. Yeah, whiteboard. New.
Does it work? Okay. Okay. So now let's see. This is our data, X, and we can have something like this. Sorry for the drawing. It's something like this. And this is MLP, is a basic structure in machine learning. And the X is 1 dimension. And here we can maybe, so the MLP will learn itself, like how to adjust the width. Oh, and then it will be 4 dimension. And also maybe the input data is not 1 dimension, maybe it's like more dimension. For example, because right here in the, still sharing, okay.
And you cannot switch. If you switch, the audience in the Zoom cannot see that.
Oh, okay, I see. Okay, I see.
You finish that, then you put some thread.
Okay, thank you. For the VQC I chose is based on 4 qubits, and then this data will go through the VQC combined with those 4 qubits. But for example, if our data is like 6 dimension, is more than 4, so we can still use MLP, or we can use some other structure, maybe autoencoder or something, to change our dimension. So I just want to mention the dimension is not the same. So before the data go through the VQC, we need to change the dimension. Yeah, I will right here. Oh yeah. Go back to here is the VQs. And then this part is the variational layer, and use the CNOT gate to establish the entanglement for each qubit. And here we can see the qubit 0. Let's say this one is qubit 0, qubit 1, 2, 3. Qubit 0 has the entanglement to the qubit 1, and 1 with 2, 2 with 3, and 3 with 1. And for this part, we already finished the entanglement. But why do we need something here? Actually, we do not necessarily need this part, but for this part, it has some advantage. First, if we have some algorithm that we need something calculate with a qubit 0 and qubit 2, so it will not go through qubit 1. It just directly calculate qubit 0 and 1. We do not need to do this. And also, if we have more entanglement, which means the system is kind of more stable. But I will say it doesn't mean that the more entanglement would make the model better. Like for example, for our neural network, it doesn't mean that more layer we have, the better machine learning model that we have. So it will cause some other problems. And right here, this is another gate. So the difference between this gate and this gate is because this gate is not learnable, because here the input is the data itself, and here the data alpha 1, beta 1, and gamma 1. This is what we're gonna learn. That we're gonna use the neural network to learn these and make this and make the whole system can solve the problem. So these, I cannot see them. Oh, these numbers are basically the same as the weight. So instead of training the weight, we're gonna train all these numbers. And after this layer, we have our we can see the result in the quantum state, and then we're gonna do the measure, and we can use different measurement to transfer our quantum data to the classical data. And for the variational layer, it does not have to be in this order. First, we're gonna do the entanglement, and then we're gonna use the gate. We can use the gate first, and also we can have a lot of variational layer stack to analyze the data that we have. So, and after that, this is how we do the optimization. And Professor Liang showed the same stuff yesterday, and I'm not gonna go through the math. And here we have the function of for example, if this observable B is the result that we have after the measurement, and this is used the expectation value of the quantum data. So, and here is the F. F we can say is the whole system that we have, but the F is not the loss function, because in machine learning we need to take the gradient of the loss function, and F is the part, or we can say an important part, that we need to calculate the loss function. So we need to calculate the gradient of F to calculate the gradient of the loss function. And here the gradient of F, that we have the X is input, and the theta I is here. These are all theta we treat it like this, and we can say the theta I is actually the weight in the classical machine learning. And here I'm gonna show the example code. Wait.
Copy the code to the.
Yeah. Okay. So so this code is basically gonna analyze the sentence, and you can see here these are the part of speech of each word. And to be simple, I just use the determinant and noun and verb. So it's gonna analyze the structure of the sentence and all these words, and then if we give the model another new sentence, maybe you cannot see. Oh, you can see from your on screen. Yeah, and if we're gonna give computer another sentence, then it will tell us, okay, this code is noun and this code is verb and this code is noun as well. So that's what I want to do. And for here, this is our training set and this is the test set. Not a big training set. I will just show an example of the structure of the QLSTM. So how the model will work is not my focus. Here, this is the part that I need to define the LSTM. This is the initial and forward. It's basically the same as classical machine learning. And here, if the qubits is greater than 0, so which means that if we have like qubits, we're gonna use the QLSTM model, and if not, we will just use the LSTM model. And for the LSTM model, because PyTorch has its default LSTM model, so I will just use the LSTM model. And for the QLSTM model, I will define it right here. But actually, if this code is based on PennyLin, and PennyLin you can just import PennyLin, but here you can actually from QLSTM PennyLin to import QLSTM. In this case, you do not need to define it yourself. You just need to have your parameters and use this model. So yeah, this is the model. So these are the initialization, and here there are wires of each gate. And for each gate, because we use 4 qubits VQC, so we need to initialize all these four wires. And the backend is like what kind of simulator we want to use. And for PennyLin, you just use default PennyLin like simulator, and we can also use Qiskit or something else. And these are the definition for each gate. And for each gate, here is the angle embedding. Angle embedding, you just need input of the data, which is this part. So this part, this is input, the x1, x2, x3, x4, they are input, and we use this input to rotate the qubit data. So, and then here the basic entanglement layers, it needs us to input the weight. We're gonna train with this weight. And here we can say this structure of VQC is not the same as previous one. So this is very basic. I think this is one of the most basic structure of VQC. So there's only one gate, and here only one entanglement, and only one gate for the rotation with respect to the weight. And then after define all these gates, and then we can have our, oh, and also for here, we can say there is a C layer. The C layer is just what I mentioned, is we need to transfer the dimension, transfer the data from 1 dimension to 4 dimension. And after the measurement, we have, for example, we have data of 4 dimension right here, and then we need to transfer it back to 1 dimension to feed the LSTM model. Because for LST model, the information will keep going through, like, this is only one block of LSTM. We have different blocks, and the information will go through itself. But for quantum data, the data cannot go back and forth. So we need to use the QLSTM, use the main structure of LSTM. So they only change this part. And after we transfer data from the quantum data to the classical data, it will just go through in the LSTM data, in the LSTM model. So go back. And this is the forward function defined for the QLSTM. It's basically the same as LSTM. The only difference is the VQC part. Here is the training, and then we train the model, train the model after. I'm not gonna train it again right here. I'm gonna take some time. And actually here you can see it's kind of overfitting because this is for the training part, and we can see the accuracy is about 1. But I just want to show a picture about training. So this is what we have. And we can see the quantum LSTM model kind of train faster than classical LSTM model, but actually it's not, because LSTM model will take only about like 5 or 6 seconds. But the QLSTM model, it took like 3 minutes. I think it is because we are using the simulator. The simulator will take some time to do the simulation of like how quantum stuff works. But we can see the epoch is less than the classical LSTM model. Here is the result. Like, for example, we have a sentence, John watched TV. And the label is like John is noun and verb and noun and the predicted value. So the QLSTM make it wrong. It should be verb. And also for the second sentence, the fox loves drinking, and they both got right. So yeah, this is basically how the model. So the main part of the model, it should be the VQC part. Others is the same as a classical machine learning model. And here, this model is very basic, and I will show another. Wait. Here is. Wait. This is the result that from a paper. This result, it used the LSTM model and QLSTM model to do a portable quantum language model. And for here is the result of both models. For the accuracy, they're about the same. QLSTM model is a little bit higher, but not that much. And for the F1 score, they are the same. And there are 4 pictures. I think the one that I want to show most is the first one. We can see for QLSTM model, it can train with much better result, or we can say less loss in 2 epochs. But for the quantum LSTM model is, but for the classical LSTM model, it's really slow. So that I think this is how quantum computing in machine learning help us. That because sometimes we need to, when we train a model, maybe we're gonna use like 100 or 1,000 epochs, but for quantum, it might use less, or maybe let's say here we only use 2. Oh, sorry. Go back. And for the second picture, I think this one doesn't. There's no information because the the data set is not the same. This one is large language model and this one is small language model. So I will not talk about it. And here we can see the difference is the blue one use 4 qubits and the yellow one use 6 qubits. And we cannot see much difference between 4 qubits and 6 qubits. It's like the classical machine learning. And because, for example, if we have let's say, have a MLP, and the first one have maybe 2 layers, and the second one maybe have 10 layers. We cannot say the second one with 10 layers is better than the first one with 2 layers. Sometimes if we have 10 layers, for example, if maybe we're gonna have some overfitting issue or some other issue because of the layers. And also the same for the qubits. For more qubits we have, it will express more information, but also if we have because the qubits have entanglement with each other. And for example, if in real life we have some noise for one of the qubit, and then it has entanglement, then it will affect other qubits. So maybe we'll have some more noise with 6 qubits. So I believe that's why the 6 qubit we cannot say 6 qubits is better than 4 qubits. And here it's the same. Although 4 qubits a little bit better, but I'm not pretty sure because it only shows 2 to 10. And maybe we change another data set, it will be different. But we can say it's close actually. So that's all that I have. Thank you. But yeah.
Okay, so I'm going to be talking about quantum general adversarial networks. So first off, what is a general adversarial network? So a general adversarial network is a machine learning network that has a component of a generator and a discriminator. The way that this one works is, unlike some of the other machine learning models that you've been shown today, the discriminator, which is basically like our error checker, gets updated real time with a separate loss function. So it becomes more accurate at telling the generator what's wrong with it compared to the real data. So a quantum general adversarial network is basically just a quantum generator and a quantum discriminator. So they work the exact same way as the standard generator and discriminator, but we introduce quantum circuitry so we can tackle different problems, and we'll get more into that. But the biggest advantage of using quantum generators and discriminators is we get to take advantage of superposition and entanglement, which allow us to check larger solution spaces faster. So this is the overview of the diagram, and we'll come back to this more than once just to help as we work through it, and that should make it a little easier to see. So the QGAN and GAN training process is identical. It is a basic 7-step process of initialization, data preparation, forward pass, loss calculation, backpropagation optimization, iteration, and then finally, we hopefully will arrive at a convergence. So our initialization step is to create our machines. So we have to build our machines based on what we want to achieve with our data. So in the example that I'll show you in a little bit, mine was entirely focused on making a circle, okay? So for that, that meant that the random noise that I was giving it, which is that step, I decided that to be all the values between -pi and pi. And the parameters, you can kind of play with those, but in the essence of what we're talking about quantum wise, that is changing the angles of our gates to alter how they affect the data. Okay. And so our real data sample is created or collected. From me, it was literally just a unit circle. And then random noise is created and fed into the generator. And like I said earlier, you can either start with totally random noise if you have no idea, or if you do have an idea of what you're looking for in the solution space that it may be in, you can feed it that, and it'll just help the generator work through its options faster. So here we have our forward pass. So in our forward pass, this is a single run through the machine learning model. So we begin with our random noise, which goes into the quantum generator. And on our first iteration, it's probably not going to do much to it. It's going to run it through all the gates that it has, spit out our generated data, at which point the generated data and the real data will then enter our quantum discriminator. And the discriminator will screen through it, giving it a probability score indicating whether or not the generator created accurate data. And so then we perform a loss calculation on both parts. So the discriminator loss is this is a basic one, a binary cross entropy function that is just taking the discriminator's discrimination and judging it on how good it was at discriminating. That's all it's doing. And then we do the exact same thing for our generator against our real data. This is just judging how well did the generator generate. We're not looking at how accurate the generator was, okay? In context of the discriminator. We are looking at how accurate it was in relationship to the real data. So that occurs, and then those update model steps is where we're performing our loss function and our optimization. So our back propagation and our optimization steps. So our quantum discriminator is updated to minimize loss using a basic gradient descent. This is calculated with aspects with respect to our parameters. And then our quantum generator is also updated that exact same way. And in this step where we're trying to minimize loss, we're also running it through optimization algorithms. And there are separate optimization algorithms for classical and quantum. So there's the familiar one with classical, the atom optimization. There's similar ones like variational quantum eigenvalue optimization, which do the same thing. They're just more applicable to the quantum space. And so then we're going to run through our iteration and convergence. So as you all know, when you're cycling through a machine learning model, you can give it how many iterations you want it to run through your model before it gives up. And that's basically what this is. So we iterate through it X amount of times, or we stop when we achieve convergence, which is when our real data becomes indistinguishable from our generated data. I don't often hit this when I'm working with it. So of course, what are the benefits of QGANs versus a regular GAN? So because of the abilities of the quantum space to have stuff like entanglement and superposition, like I mentioned earlier, we can more efficiently search large spaces, which is a very big benefit when it works. We have improved optimization because we have these algorithms now that are quantum-based optimization algorithms that can more efficiently work through our loss functions and find faster and better ways to optimize our data. We have enhanced representational power. This comes from the idea that quantum scenarios are better at looking at complex equations, complex system designs, and breaking them down to solve them. And again, this is because of our quantum parallelism that we're able to do this. Like I mentioned, our complex data structures, quantum systems are inherently better suited to look at these and solve these structures and relationships. The biggest challenges that come with QGANs at the moment are, of course, we're limited by our hardware. As you've heard a lot about, we've had several different fields of hardware going right now, but we still need to work on it in a big way to get to the level where we're able to efficiently use machine learning in the quantum space. Quantum and classical integration, as Ben's going to talk about, the hybrid quantum classical space is not very active, like as far as getting those classical to quantum connectors. And so there's a lot of holes in that prevent us from being as efficient as we can with QGANs over just GANs. Algorithmic design, again, not a lot of research in that field that's like breaking any boundaries. So we're again limited by our knowledge there. And then of course, benchmarking and validation, like with all machine learning stuff, it's difficult to demonstrate a clear advantage. Like we can look at it mathematically and say there should be an advantage, but with our hardware limitations that we have now, with the algorithms we have now, we are hard pressed to show a clear technological advantage. So that was a really fast run through. But that does give us time to work through the coding. So if everybody wants to go here, this is a Google Colab folder that I put together, and I'll open it too so we can work through it. But this is a quantum generative adversarial model. Now, you will probably notice there are some gaps in here, and so just gonna kind of work through these, and we do have TAs, right? Dr. Yang?
Yeah.
Awesome. So yeah, there's 1, 2, and then there should be a third somewhere in there. We'll find it if it doesn't work. But yes, so the first thing that we're gonna do is we are going to build our generator. So still screen sharing right now, or awesome. So you guys should all have that pulled up, and I'm gonna pull up my answer key so I can work with you guys through it. But does everybody have access to that? Okay. Awesome. Everybody can see that now? Awesome. So I'm just gonna come here. This is my master copy, and feel free to copy it down, but I just wanted to walk you guys through the most important parts of this. So for this first part, of course, that one is the minutes up.
So this is Penny Lane, right?
Yes, sir.
Okay.
This one is the Zoom seeing the workshop model right now?
Yeah.
Awesome.
I can see it.
Okay, so for this first step, and you guys are gonna have the benefit of seeing both of them, but yeah, I would like to explain this part. So the first thing that we're gonna do is we're basically just applying our Y gate to the function, and this is just applying variation throughout the layers. And so this is what is basically going to act as our generator's parameters that are going to shift while we are training the model. Okay, so under that, and I guess I will share the screen for this one.
So you're using 2 qubits, right?
Yeah, so we're using 2 qubits, 6 layers, and then we have our parameter vector, which is what's going to be actively updated each iteration. Okay. So yeah, if you guys want to fill this in, and I kind of wrote most of it in the comment there, so you should be able to figure it out, but you're going to use this QML object. So Penny Lane is this amazing thing where you can set up a quantum machine learning node basically, and then you can treat it like you would programming it like a quantum computer. So if you access that QML, and then, and I'll share this screen with the Zoom too, just so that everybody can see it. So yeah, you're gonna want to, if you put that into your code, okay, and you do not have the link for this one in the chat on purpose because I would like you guys to work through it so you can hopefully better understand it. But this is what's going to kind of act as what's going on inside our generator circuit. So in that diagram earlier, what we're building right now is our quantum generator, okay? It's a very simple design, but you don't need it to do much because all we're having to do is design a circle. Okay. And so then as we go down, our next stop is going to be our optimizer. So here, you're going to create a gradient descent optimizer. It sounds really complex, but thankfully, with stuff like Penny Lane, we are able to, actually, this is a Keras package, you know, okay. You're able to just put in a single line of code and run through it. So our optimizer is, again, we're taking advantage of that quantum machine learning, and then we're just going to put in the gradient descent optimizer, and then you can set your step size to whatever you want. I was just using mine really small. I just wanted to see what how it would change the data I was getting out. But this is what's going to act as our optimizer, which again, is going to feed back. It's going to take a look at those loss algorithms, and it's going to feed back both the quantum generator and the quantum discriminator separately. Okay. And so I believe that should be everything. If it doesn't work, then I'm in big trouble. But yeah, so if you want to load those libraries up and try it for yourself, what you'll see is hopefully something close to this. So the pie plot itself will draw a whole circle, and then you should get points. Hopefully, if I did it right, that'll appear on that circle. And that is the generator trying to mimic the real data in the process of the QGAN. So it won't give you like a perfect circle. And I think I may have. Yeah, so it won't give you something like this. I know it looks ovular, it's just because the scales are messed up, where it has a point at each point. But instead it will give you something like this. So you'll notice we have a little bit of convolution and stuff, and that can be ironed out with further training and different loss methods. But what's happening is that our QGAN is getting data that is correct. So I didn't include any function when I was building this that would like remove duplicates. But so that's why we have some stacking of points, but still we see that it does create points that are entirely on the circle. Okay. So is everybody able to do that? Good. Awesome. So yeah, that is a basic walkthrough of the quantum general adversarial networks. Anybody have any questions? Cool.
Yes, I have need to use this. Okay, here we go again. So it's a little bit more advanced techniques when we work with the quantum convolutional network. You remember yesterday I mentioned about the quantum secret with only work on 8 qubits, because in the real world we have an image of there are some 28 by 28 by 3 pixels, right? And if we multiply by this, we have to prepare about 1,000 qubits to run that this algorithm, right? So if we don't want to run with 1,000 qubits, right? So we can do it that we just need to extract the feature of the image, and then we put the feature into the quantum circuit, so that we can reduce the number of the qubits that we need to run the algorithm. So this is one approach to run it based on the Qiskit. So first we have an image that has 28 by 28. So we put it into 2 convolutional and max pooling, right? We put it into 2 convolutional and max pooling, but it's still, you know, that because 16 by 4 by 4 is still there, maybe around 100 qubits, right? So we still put it into the fully connected layer to reduce the number of the feature that we put into the quantum circuit. And lastly, we just only reduce it into 2 qubits, right? And we put it into the estimator QNN. So on Qiskit, we only have 2 algorithm QNN algorithm. One is estimator QNN, and the second is sampler QNN. So we don't have many choice on that. So after that, we measure the last qubit and we get the result. Yes, that's the way we you know, encounter the problem of the real world scenario when we work with the quantum circuit, right? So I will give you the result here, and we put this in the Zoom. Okay. So in this tutorial, I just classify 2 digits. That is 0 and 1. Yes, you can change it into 10 digits if you want. It's simple. Okay, so this is the quantum circuit on that. You remember that the G feature map to encode the classical data to the quantum circuit, and one is the real amplitude. This is the parameterized quantum circuit to adjust the parameter when we optimizing the result, right? And the problem is that how can we interpret the quantum circuit into the bytecode, right? So we have to use a module that's called talk connector, right here. Yes, you build a classical convolution neural network, and then you also build a quantum neural network. Then you use a talk connector to connect from the classical to the quantum circuit. And then I put it into one classical neural network to calculate and give the final result. And you can see all of the steps right here. All right. So the accuracy is 100% because this is an easy task. So one question is that can you believe that the quantum circuit on the quantum machine learning can bypass the classical machine learning? Yes, I don't think so, right? And I think that most of you don't think so. But why we have to do this, right? One recent paper showing that the state of the art when we classify the mnist digit number is let me 99 by 98 by 86%. And if we use the hybrid quantum convolutional network, the accuracy increase into the 99% with 8 times weight. You know that because the classical is more than 8 times comparing to the quantum hybrid network. Yes. So imagine that it's just a small number of weight. But for the large language model, we have maybe 20 billion weights, right? And if we can utilize the quantum power, we can reduce the weight and we have something like more powerful tool on that. But you know that it is the future. So for example, like 30 years ago, who gonna know that the AI will have a huge impact as today, right? So we are at the initial step, and as a researcher, we have to figure it out. We have to figure the potential of the quantum. So that's why we have to do something like this. Yes. Exactly. Yes, the classical, the accuracy of the classical algorithm on mnist digit is around 98.86%. And the state of the art at the right now for hybrid quantum convolutional network is 99%. And they just use less than 8 times weight. You can think about the theta, about the parameterized quantum circuit, comparing to the classical. So we can reduce the number of weights on that. And one thing is that we are in the NISQ. NISQ era of today, you know, at the moment in the NISQ, this is noise intermediate scale quantum. We work with the quantum many noise. So you can think about that when we work with the theory, we just have one result, right? Based on the probability. For example, if you can make sure that there are 100%, only 100% have this result. But when you run on the real quantum machine learning, the real quantum computer, you will have something like 10 or 20%, 20 order result comparing to that, right? And I run the rover. I think that Dr.
TLE know the global algorithm, but he didn't have time to explain about this. Yes, so I run a Grover on the simulator. They only give one result. But when I run on a quantum computer that have 20 qubits, the real quantum computer, this is yield maybe around 20 results. Yes, that is the problem because we have to deal with the noise. And this 99% it runs on the noise quantum. They claim that. But I didn't know that. They just claim that they didn't propose their algorithm because this is relating to the money, the commercial approach or something like that. They just keep it secret and they claim that, right? So this is the problem why we apply the quantum on quantum machine learning in this field. Yes, and that's my talk. Thank you so much. Yes.
Metric is accuracy, but with that, does it also speed up the time of calculation using the hybrid method versus?
Yes. The purpose of using hybrid model, we try to reduce the number of qubits that we use in quantum in variational quantum algorithm. Yes. So I mean that instead of you have to use 1,000 qubits, you apply the classical method to reduce the information that's the quantum circuit unit to maybe around 10, 20, something like that. Yes, and they are still developing some other algorithm to mimic, to optimize the number of qubits, right? So to that minimize the number of qubits, but they still have a best result. Yeah, this is the trending in quantum machine learning right now. Optimization, yeah, that's all. And how to work with the real quantum machine learning in NISQ era.
I don't know if it was the question, but what I understood is like, is it faster? Is it like the quantum version? Is it faster? It's the same.
Yes. It's not faster because because when we mention about the faster things, right? Somebody will misunderstood about the faster definition. When you work with the quantum, we mentioned about the complexity. We usually mention about the complexity. For example, if the complexity of this algorithm is 2 to the n, right? For the Grover, you know that the Grover will have the complexity 2 to the power 2 to the n power, and for the quantum, we only need square root of n. Yeah, and if we use quantum, we mentioned about faster because we use less parameter compared to the classical. Yes, and calculations or the calculation or something like that, it may be still the same because it's a linear algebra, right? Yes.
Hey, hello everyone. In this session, I'm going to summarize the previous presentation. If you remember, in the last session, I designed this data set. We had two features, X1 and X2. Then we applied this X1 and X2 to two qubits, Q1 and Q2. Then we designed the quantum circuit with two trainable parameters, theta1 and theta2. So, for example, consider this. This is our quantum neural network. So at first we want to feed Q1 and Q2 to this neural network. Then apply this X1 and X2 to these two separate quantum qubit. For example, we use the RY gate, which, for example, if the input qubit has a ket 0, then we rotate around the y direction. Then after this transformation, we apply our x1 and x2 on our current qubit. So after this calculation, we will have these three possible output 0, 0, 0, 1, 1, 0, and 1, 1. But after the execution of this neural network, we only have one state. For example, 0, 0. This is the result of the one-shot execution of this quantum neural network. But in reality, we, for example, run this quantum neural network 100 times. After running 100 times, we will have this probability distribution. For example, 0, 0 has 10%, and 0, 1, 20%, 1, 0, 30%, and 1, 1, 40%. But our task is finding this theta 1 and theta 2, because if we have these two parameters also, our problem is closed. Then we can feed this data and find the output of this quantum neural network. But how we can we evaluate this theta 1 and theta 2 with forward and backward propagation and find the minimum of our loss function. But in this session, I'm going to talk about the two main chapters: classification with real data, iris dataset, then trained our model and design a simple classical neural network and training, and then design another quantum neural network and training with the same data and compare the result to each other. Then design a generative adversarial network, which Joseph show us the detail of this quantum neural network. At first, I show you what is the meaning of the classical GAN. Then I designed the quantum GAN, which includes two main parts: quantum generator and classical discriminator, which is in fact, the hybrid model. Okay, this is our data set. We have four main features for this data set: sepal length, sepal width, petal length, and petal width. Then we have three classes: class A, class B, class C, which is the type of this flower. We want to train our neural network, classical neural network, and quantum neural network based on this data. Okay, based on this data, we cannot separate and classify this data based on the main features. For example, if we consider the petal length, we can separate this class 0 from these two data sets. But if we want to classify class 1 and 2, there is an overlap in these two cases, but then we cannot separate these three classes based on the main features. So we should design a neural network to resolve this issue. For data pre-processing, we only do the simple task: normalize data with min-max scalar, split data 80% train and 20% for test. And this is the feature map, which is the task of the feature map is grab for example, x1, x2, x3, x4, and load on the current 4 qubit. And after that, this is a trainable quantum neural network, which, if you remember, for example, in the previous example, we had two theta 1 and theta 2 as a parameter. Our task is finding this theta. But for this neural network, we have 84 trainable parameters. 84 theta.
Only show like 16, right? 16 parameter. Only 16 parameter here.
Oh, yes. For here, yes. Okay, then the result is, for example, for after train and test the classical neural network, the training score was 99 and the test score was 97, but for the quantum neural network, we have 85 for train, and for test, we have 87. I shared this link after already with you in the chat. Okay, and in this section, we are going to focus on the QGAN. Okay, in this slide, you can see how we can implement the forward pass of this GAN. For example, let's start from here, from the noise. Based on the noise, the generator generates some fake data, for example, the picture of the dog or cat. And also we have the training sample, which is real sample. This discriminator should find which data is fake and which data is the real. So we can, for example, generate one loss function, or we can generate or consider two loss function. In this example, I used a two loss function for this example. But the QGAN structure is similar to GAN, classical GAN, but we should modify this section. So we remove this section and we, instead of using that noise and generator, we use the quantum generator, because quantum operational measurement inherently have noise. But in this case, we are using these noise to feed the generator and generate some corresponding picture, for example. And this is 4 tasks that we should consider to implement the quantum GAN. At first, we should design the quantum generator. Then we should define the classical discriminator as a PyTorch-based neural network. Then we should wrap these two, generator and discriminator, with the PyTorch approach. Okay, for example, this is our data. This is a 2D normal distribution. So, for example, at each edge, we have 8 elements. We consider we have 8 elements. Then finally, we have 64 elements as output. This 64 is equal to 2 power 6, which means that for this quantum neural network, we should feed 6 qubit to our neural network. This is the dimensional parameters of this neural network. For example, and this is a structure of the generator of the QGAN. As you can see here, we have 6 input. Then after running this code, we will have 64 possible outputs. This is the result regarding to training and the corresponding KL divergence. And this is the loss belonging to the generator section, and this pink one belonging to discriminator loss. After, for example, 50 epoch, for example, we will have the hash point, which we define based on the game theory. So, for example, this is our saturation point. Okay, and this is the output of this quantum neural network. For example, this is the true PDF, true normal distribution, main and real data, and this is generated data based on the quantum neural network, and this is a difference between this generated and this predicted neural network, and this is the same result, but in this case we are using the cumulative distribution. And this is the corresponding link for this QGAN.
You copy the link to the.
Yes, I already copy this to.
Hold on.
Okay, as you can see, for the first example, we load this iris dataset. Then I print this dataset. For example, we have 4 distinct features as input. Then in this, for example, we extract and apply features and label, then normalize our data. This is a visualization of this data. Then split data 80% for train and 20% for test. And then train data based on the simple support vector classification. Then evaluate our model based on this classical model based on this data, and then define our quantum circuit. Then define the ansatz, which is trainable quantum circuit. Then define the optimizer. In this case, we are using the Kobila, and then create a sampler class, which is inherit from the sampler V2 main class. I described it in the previous session. And this is the callback function. We show the training section live, and train the and this section you can see the train, and this is all, for example, the loss function based on the epoch, and this is the test and training score for this example. And for the last one, we are going to use the QGAN, install the library, and then the setting of the random seed to have the same distribution after each run, and define the data here. And here, this is all the data set that we are going to train our model based on this data. And this is a feature map of data which assign each feature to the corresponding qubit. Then define the quantum generator here, QNN sampler. And then define the PyTorch classifier, PyTorch discriminator here. Then create the generator and discriminator here. Then define the loss function based on that generator and the discriminator, and define the optimizer here. And for example, assign the corresponding learning rate for this calculation. And this is the training part of our model. Okay, as you can see, after each, for example, 50 epoch, we have the saturation point. And this is the result of this code, which is the cumulative distribution. And this is the probability distribution after running this code. Okay, thank you so much.
Okay, you will go to the certificate part, or just a copy or TO? What's your choice? Okay, it's great. Right. Great? Yeah. Okay, 5 minutes. How many minutes? 5 minutes? 10 minutes break. Okay. And what's the colonnade? Colonnade. Okay. Yes, this is an architecture. Yeah, exactly. So you have also figured that. Yeah. Register and these, right? But it's basically. I'll take a picture and I'll put that on the same thing as that. So maybe you can do it. I think, yeah, probably that's me. One by one. And then. Why don't you send it out? It's like, oh, you can't download before the song is yes, you see. If the easy stuff, right? No, you got it. It's not easy. Too many. The more you got it, so thank you for doing so many changes. Yeah, that kind is when you work one day. Well, you guys saw it, right? We're working on the. Once you know it's can you everyone's into focus on the you come over the product.
What do you want to do?
This is the caller name, okay?
Oh, okay. Oh, I said it.
You want me to?
Dr. Mentab at first in grade school.
I thought enough of, oh, why not come on? I want to take a picture. To NSF, so.
Did you get it?
Okay.
Amin?
Amin, come over.
Oh.
Yes. You should come over.
Yeah, you should come over, each participant. Get closer, Elena, please get closer, 2 seconds.
Every one of.
Yes, everyone.
Please. Do you really need me to be the people?
Elena?
Great, thanks. Thanks for being.
No, Elena, beside, stay beside, stay there in the picture. No, the three of you, don't.
She's like, yes,
Please,
inside. Okay. One, thanks.
Can?
No, it's a pen, right? Okay. Oh, Lena? Yeah. You guys, how about the outstanding baby game or start? One, two, three. Thanks. Okay, you guys come over. This is the okay. Both Lee and Elena, you can stay there. Okay. One, two, three. Yes.
You got it?
Yes, I got it.
Patrick.
Patrick's been at the beach all the last 3 days. I don't know.
Yeah, Patrick is a science thing from TDA. And Patrick in the middle, yeah. One, two, three.
Thank you. Dr. Ma.
Oh, we have a little bit. One, two, one, two, three.
Dr. Ma.
One, two, three. Thank you.
Carla Emerson.
One, two, three. Thank you.
Manisha.
Manisha.
Hey, there's water in there. Did you find that?
One, two, three. Thank you.
Shari.
Thank you. Okay. One, two, three.
Nicole. Nicole.
I think you'll probably be the next one. Later. Yeah.
Did I say your name right? Nicole.
Nicole.
Okay.
Yes. Yeah, he's a high school scholar, right?
Yeah.
From Macaulay.
Right.
Yes. One, two, three. Thank you.
Akil. I know how to say the name, right?
Yes, Akil.
Akil. Wes?
Yes, please take picture. One, two, three. Thank you.
Andrew Adams.
New Cedars.
You got one there? Okay.
No. Gonna have his own.
Oh, I see.
So.
Yeah, we can give it.
Philip.
Yeah.
Yeah.
Two, one, two. Thanks.
Thank you. No problem. Summer.
One, two. Thank you.
Hong Ming. Mengjun.
Yeah.
Dr. Jiang.
We have another scientist from
TVA.
TVA, yes. Okay, 1, 2, 3. Thank you. Thanks.
Megan Burns.
Okay. 1, 2. Thank you.
Bansari Patel.
Sorry.
Is that Bansari?
Yes. Sorry, yes. 1, 2, 3. Yes. Thank you.
He's a professor with Chat State. He's not here.
I see.
Wesley Foster.
Okay, Wesley Foster.
Yeah. Razani. Badala.
She left, but I can take that.
Okay, okay, I will just put it here. Nur? And you?
Oh, Dr. Nur, yeah.
Dr. Nur?
Dr. Nur, yes. I think Dr. Nur is a double E, right? Electrical engineering. So, yes. Thank you. 1, 2. Thanks.
Raga. Raga.
Oh, he was here for the whole day, for the whole 3 days, yes.
Joseph. Joe.
One, 2, 3. Thanks.
M7. Bakia.
Not good.
Yes, I'm sure he's having that.
Yeah, he is not here now.
Oyango.
Yes.
Oh, okay, Dr. Oyango, okay.
Yeah, she was civil engineer.
Oh, okay.
Yeah.
Edward.
Oh, Edward, oh. Thank you. 1, 2. Thanks.
Eric, what? Eric is not here.
Eric?
Yeah.
Okay.
He's not here.
Mhm.
He's a computer science major. Matthew Root.
Oh. One, 2, 3. Thank you.
Gage.
Okay. Oh. Yeah, thank you for staying with us. Because of his, I think the appointment with friends, right? Thanks. 1, 2, 3. Thank you.
Just want you to know he's risking his life taking my car.
Yeah.
He did that just for you.
All right, next one. James Cummins.
Oh, James.
James Cummins. Okay, let's see. Dr. Wu.
Yeah, Dr. Wu is the co-PR this workshop.
Okay.
Yeah. One, 2. Thank you.
Shara.
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 Thank you for waiting, Sarah. I know there's some other. One, two, three. Thank you.
Presents too.
Which one?
Presents, I can take it to her.
Oh, this one? Your mother's one?
I think I'll.
Yeah.
Coming back.
Oh, she's back, right?
Many,
Money.
many.
One, two, three. Thank you.
I'll, how do I?
Yes, our speaker, right?
Yeah.
Cybersecurity. Okay, one, two, three. Thank you.
Andrea. Navarro.
Oh, yeah, she is not here. She took it online. I can.
Oh, Andrea. Maxwell Cannon.
Maxwell.
Max, well.
Not here.
Online attendee.
Probably. Maxwell King.
Dr. Cox. Why Dr. Cox has Dr. Cox here? I have doctor here, doctor. So we might should say Dr. Cox.
That's right. One, two, three. Thank you.
All right, you will have a doctor too.
Okay.
Oh, I signed this for you. You cannot do it.
I'm in the middle, okay?
You cannot sign on yourself. So
No.
Thank you.
Can you take a picture?
No, I do not want me. Thank you.
Oh, yes, yes.
I'm Dr. Yang, she's not here.
Yango? Yeah, Dr. Yango, that's.
Okay, and you, right?
Hers is right here, right here, right here.
Okay, when you take picture.
Yes, yes. Thank you.
You get to.
Yeah. Thank you.
All right.
Thank you. Thank you. Okay, now let's start the talk. We are going to give our the closing remark. Okay, the closing is the talk about this workshop. Okay.
Wait a second. Don, come over. How do we, this is the, come over? Yeah, it's the computer, right?
Yes.
Should be sent it to his Gmail account.
Yeah, in my Gmail. Yeah, I'll go to it.
Yes, just go to the Gmail and still this process.
Yes. It's here, right? I will download it.
Okay. Very good.
Oh, why it's the, give me a second.
Okay.
It's hard to get it. It's the download, right?
Yes.
It's this one, download.
Yes. Yes.
Why
Okay,
is it-
I will do it. Because this is the PDF, so
Open with open with, okay,
Yes.
right? Accept. Okay.
Excellent, thank you.
I will leave to you.
Yes,
Are
sir.
we on Zoom and
Did
everything?
you
Is that
share
all set?
the screen was shared?
Yes, I
In
will
the
share
chat,
it.
in the Zoom.
Here.
In the Zoom.
Zoom. Yes, I already opened it. Yes, sir.
And the sound is on, looks like the
Yes,
audio is on and everything. Very good. Okay. I have 9 slides and I will not go through them over a long time, I promise, but the most important one is this first one, I believe. See if I can advance this. There we go. This is the acknowledgement slide, right? I'm repeating what it says on our website. We thank Eva Hunter and Kim Sapp. You probably saw Kim out here a lot, making sure the food was all here, hugging people, making us feel welcome. She's an amazing woman, and we thank Eva and her and the other folks who helped with websites and designing and everything. Reinhold Mann, who you saw come in and out, he's a very busy person, but he really was kind of the moral support for this whole thing. All right, he's really one of the key people pushing the whole quantum initiative, and as a PhD physicist, you know, it's really a heartfelt effort for him, and we all appreciate that. I want to thank all of the speakers, especially the students. It is not easy for you to get up in front of a group like this if you haven't had a lot of speaking experience. So I think we got to give the students a hand for that. So it was listed on the website that the co-organizers were Dr. Lee and Dr. Liang and myself, okay? And I know Dr. Lee did a lot. I don't feel like I did a whole lot as far as organizing this, but I want to thank Dr. Lee. He's really the spearhead from the science side of the quantum effort here. We're so lucky to have him, and it was really fun to teach with him. It's just, he's a remarkable person to have here with us. So I want to thank him. And I really believe, I think, as you saw, Dr. Liang is the one that really pretty much put this workshop together, I think. So let's give them, both of them, and Dr. Liang. We all agree, I think it's a good success. I wanted to give credit where credit's due, of course, to put this on a slide to show you the books that I use, some of the key books that I go to. There's several others. There's a ton of books out there. But the Mike and Ike book is the first one. It's a very good reference. Dr. Lee actually is the one that exposed me to Hidari's book, which I've used a lot. I referenced that a lot. The book I'll probably use this fall, or I'm not requiring it for the course I'm teaching this fall, which I'm going to shamelessly plug in a minute, is the book by Larkowski. But I chose that because he's a physicist who teaches this at the undergraduate level, okay? And it's a decent book. I used it when I outlined the syllabus for the class, but I'm gonna veer off a little bit based some of the things on things that have been talked about here. And I like this book by Griffiths and Schroeder as well. That's mentioned a lot and referenced a lot online, okay? So I wanted to give you that. And I just wanted to say a few things in general about the quantum initiative if you're not familiar with it, okay? It's a pretty remarkable thing. I mean, a lot of research just initiates within universities, right? People say, well, why are you doing that? And maybe because a particular professor is interested in it. But the quantum initiative in Chattanooga really came out of the community. It's pretty remarkable how it grew. And it started with EPB's interest, I think. And there's actually in the community, there's actually a quantum committee that's headed by one of the members of the Brock family, which is, so it's not something that just the academics decided they wanted to work on. And it shows a lot of foresight. It's like the second generation of what happened with optical fibers, 20 years ago, right? And so it's pretty amazing where that came from. If anybody asks you how it started by community demand. All right, and we were very fortunate enough to be here to get involved with it. So this was a press release that came out a little over a year ago. Before around the time there was a big meeting here with QEDC, right? And then there's we have a website. If you just do a search on UTC Quantum, you'll see this UTC Quantum Initiative website. So if anybody asks you what's the quantum effort like or all about at UTC, just tell them to Google UTC Quantum and look that up. So check that out. So as I said, I'm going to promote the educational aspects just very quickly. It's been mentioned that we have a 4-course undergraduate certificate in quantum information science and technology. We offered the first course, Dr. Lee and Dr. Liang and I, actually, Dr. Liang and I taught two or 3 weeks of parts of it. Dr. Lee taught the brunt of it. But it was cross-listed, and at that time it's 3999R because we didn't have it formally in the curriculum yet. But from now on, it is officially there as 3810. Okay, that's a good course, the good introductory course. These don't have to be taken in order by any means, but these are the 4 courses. In the fall, and I have another little more information about the second class that I'm teaching, and then there'll be the physics focus that Dr. Lee will likely teach, and Dr. Liang or his colleagues, one of his colleagues would teach the introduction to quantum computing class. Okay, those will. So the math one's being taught in the fall. Probably next spring. What will we do in the spring? The physics one, Tian, do you think? Will the physics, the 4810, will that be offered maybe next spring?
Yes, will be offered next, yeah.
And computer science will be offered soon after that. If not, then the plan is to have all 4 courses offered in a year, so a student can take 2 each semester and get through the whole certificate. Okay, that's the idea with this. A little more information about these courses is that we had 18 students enrolled in the course in the spring, plus a few graduate students that sat in on it. And I've got 12 now registered for the fall class. And I have a picture of a learning curve I was going to show you, but I don't know if I'm going to put it on the record or not, but it is true. I have a learning curve of my learning in quantum science, and it's an exponential curve, and my dot is down at the bottom of it. Okay, but I knew even less when I wrote the syllabus for this course. Okay, that got passed through, and so I've modified it a little bit. I was pretty tough on the prerequisites. I have linear algebra, differential equations, and Calc 3 as prerequisites, but it says or department head approval. Well, do you know who the department head is? It's me. Okay, so I promise if you come talk to me and say I'm really interested in this, if you help me a little bit with some background, I'd like to know what you know already. But if you're on the edge about taking this class and want to know more about it, please come talk to me. Okay. All right, that's where it's at right now. I think it's going to be an interesting class. I told the bookstore there's no required book. A recommended book might be Larkowski's book, like I said, because it's aimed at undergraduate level. But I'll help you find some information. There's a ton of free information out there. You can go to many of these books, like even Larkowski, and look in the appendix where they often have math background, or it'll say linear algebra background, and look that up. And then that'll help steer you towards maybe some things to fill in a little bit, or I'll help you with that. We also have some courses already on the books before we even set up this certificate. There's a physics introduction to quantum mechanics class. There's a computer science, quantum computing for computer science class at the graduate level. So please keep those things in mind as opportunities for you. I made this chart when we had a workshop last month to talk about where the quantum initiative is going here. Just wanted to point out we're doing a lot of things on the education front. You know, one of the community drives or needs is to educate both students like you, but also educate the workforce, right? So that's mixed in here. And you might even see on that timeline that we have outreach to high schools. And we have some high school students here, right? So we're planning on having things like a quantum camp, which will be really fun. So we have some really exciting plans ahead of us that we're involved in. So we want to reach out to pre-college, college, people working at Volkswagen and other TVA and other places. So there's just a ton of opportunities here for us. Okay, so 2 more slides. This is the planned curriculum development. We currently have, if you don't know it, there's a PhD in computational science here. There's several PhD students here right now in the different concentrations. And we're planning on introducing one in related to quantum. Okay, so hopefully we'll get that going in the next year or two. Computational quantum science is somewhere on that timeline I showed you. And we want to work with my math department wants to work with the physics program to develop an interdisciplinary mathematical physics concentration in our Master of Science degree. So that's on the horizon. we envision having concentrations in quantum information science and engineering in our current bachelor's and master's programs. And it would help to have demand from students for that, right? When are you going to have more quantum courses? When can I get a concentration in that area? So be thinking about that. And then there already is approval for a concentration in the physics bachelor of science program. That'll be kind of the model for it, that we do one hopefully in math and hopefully in other departments as well. And we'll have to develop new courses to meet those concentration needs, which I'm excited about. All right, last slide is just to thank you. This workshop wouldn't be here without you participating in it. So we had a good turnout. We had what, 50 or so participate?
Registration is 80.
Yeah, registration is 80. That's wonderful. So each one of those will benefit one way or another from this. And I sincerely mean, we look forward to exploring the wonders of quantum science with you. It's got to be something we do as a group and collaborate on. I've always loved interdisciplinary research and teaching, and I don't know of anything that's more interdisciplinary than this. It's fascinating, and what I like obviously is it needs a lot of math. Okay, but I love teaching it and working with it, and helping students learn, because it forces me to learn too, and I like that. But please, as you go out, please spread the word about what's going on here, so we can keep growing and keep thriving and keep doing what a university is supposed to do. Okay, so what's next? We're supposed to hang around and network, is that right? If we want to? And talk?
And talking.
And there's hopefully some food left out there, okay? But let's give ourselves another hand as the thank you, okay?
Thank you.
Yeah, it's very tight. Yeah, I actually have one.
Thank you for showing up. I will see you Friday.
Your name and.
Thank you so much. Maybe next time you don't have it. I know it's sacrifice a lot, right?
No, it's okay. I just have to take off today, so it's really no big deal. I did want to ask, are you gonna send the pictures out to everybody and everything? Okay. Also, update you on like the money and everything. I think it like $2,000 more dollars.
You have not got, you got.
I've got
You got.
1,005.
Yeah.
I just wanted to update you on that.
Yes.
Coming in chunks.
Yes, it will be that.
Yeah.
Some students are coming for us, and generally we don't want to do that, but no efforts.
Yeah. Yeah, I definitely still plan to keep on going whenever the fall begins to make time and everything. But yeah.
Are you interested in the master program?
It's kind of selling, but I'm not really sure exactly what I want to do with it and everything. I thought this workshop was really interesting. It definitely opened my eyes and like that. Is the master's program only in data science or?
We have some data science.
Yeah. I'm considering a master's, but I'm also not quite sure if I would do it here or if I would do it in computer science just to diversify my like education resume. But I definitely would want to do it. I heard about all the benefits with like just the researching thing. I also would like to broaden my education just with research and things like that. Yeah, I remember you were doing the music research.
Yes, we are doing the music. Yeah. One project. We have several projects.
Yeah, if I have time, maybe I would like to do that also in the fall. But honestly, I'm also going to be taking 6 classes and my internship, so I'm
in the TBA, right?
No, I work at UNA.
Oh, UNA. Oh,
yeah.
My wife.
Yes. Yeah, I just work more in a business data analyst role, but I do want to one day move more towards like a computer science internship. So I'm still going to try to like apply to those more. But they're only weekly over here. Yeah.
Okay, thank you. Thanks for coming.
It was really fun and exciting.
I know the young people, they like to go to the beach, right?
Oh, no, it's okay. It's okay. I didn't plan it. I knew the dates were here, so I just went to the beach like right before this.
It's good.
Yeah.
Yes, we can become very good in science.
Yeah, definitely. It definitely does intrigue me. So.
I hope even you go to the UNA, keep on,
yeah, I know.
Learning something new.
Definitely. Yeah, I do a lot of insurance, sales reports and everything. I work with Excel all day.
Reporting.
Yeah, I do a lot of reports.
Probably because AI become more and more stronger, right? Who knows, in the future, maybe a lot of human work might be replaced by the AI.
They're actually said that they're implementing AI in some regards to it, but not in the department that I work in. But I would have loved to have an internship that specialized in working for that. But for example, they have maybe just business people though in their company. It's really hard to get a computer science internship there, most sadly. But honestly, with all the stuff in my resume being computer science, that's why they like me. So I don't know.
Yeah, you can try to graduate into the machine learning. I think the I know they have a lot of very good science.
Yeah, that's true. And they have a really good intern program to do job shadows within the company and to work under. And they have like a program where if I work there for a year, then I could just move to another department. But I also am thinking of moving back potentially to Nashville and everything. And they have a lot of data scientist roles there, like et cetera. There's like a Schneider Electric in Franklin and everything, a huge global company where they have a lot of data scientists. But yeah, I'm not really sure yet, to be honest.
So you're on you're already on that track.
No, I guess I definitely am planning for that, but I'm not sure what exactly but I'm still, I thought this was really cool, and I really liked the quantum cybersecurity interests me more, honestly.
Really? That's
yeah,
good.
and I've never really taken any cybersecurity classes.
You never take any? Yes, you can talk. Yeah, you can talk with Dr. Xie, Mengjun Xie.
He was my algorithm professor.
Okay, I see. Yeah, he is the director of the cybersecurity center. I think they asked him.
Yeah, I remember Major said he was doing his thesis with him.
Yes. Yeah. Dr. Xie is the major.
Yeah. It definitely did sound interesting. I think about encryption from like basic operating systems. We're not too far out. But yeah.
Today's good, right? Today's good morning.
Not everything. I think it was really well organized. So also, thanks for inviting me here.
Thank you. Thank you for joining us.
So welcome. Carl Adamson. Nice to meet you too, yeah.
Yes, I will.
Yeah, the concentration camp, yeah. Yeah. The computer science part of it, so what's part that kicks my butt. The math part, I got it. It's nice to meet you.
Probably is the one that I have the PDF, you know.
So like that, I'll start with like 15 now, right?
Maybe later, like, yes. Yeah, I have worked together for a whole year. Thank you.
We're still good for PhD qualifying exams, like the second week of August.
Second week of August.
Yes, like towards the tail end maybe. Written exams, but I think he said something about the week after that.
Wherever you're ready.
Oh, okay.
Then you find somebody to
Yeah, yeah. He said something like I do that up in Murfreesboro. I don't mind coming down here for it.
I'm okay with this.
Okay.
I don't have the exams in the queue.
Okay, okay. Is that how that works? Okay.
Don't worry about it.
Okay, I'll send you an email to remind you.
I remember that in the class, the legal term exam, second term exam, right?
Yes, okay, so I'll go over those again.
Maybe a little bit easier.
Well, I'll go over it again and again and again. I've got a trip to Memphis on tomorrow, so
I never worry because you never miss any of my class.
well, no, but it's because I can't. I'm the student that can't miss a day, because if I miss a day, I will I'm lost for the rest of the semester.
In the beginning, I'm a little worried about it, my student, but you never miss.
Oh, yeah, I can't. I'm like, I tell my students the same thing. I'm like, you cannot miss a day. If you miss a day, you're done. You can't make that up because you're not going to. You're gonna let it slide, and then you're not gonna understand the next thing, and then you're not gonna understand the next thing, and then you're not gonna get caught up. I'm like, this is just how it works. Anyway, yes, I take my own advice.
Yeah, no problem.
I don't care about